Great, I think we are live. Welcome everyone out there in Julia land. Really excited to be organizing this JuliaMolSim mini symposium this year. And thanks a lot to everyone who's contributing and listening and has helped organizing behind the scenes. So it would not have come together without everyone's help. So really grateful for that. I'm Dr. Rachel Kurchin. I'm a postdoc at Carnegie Mellon. I'm actually starting a research faculty position here in the fall. And I'm really excited to be sort of emceeing today and taking up the first bit of the presentation time. So the first little bit of this is just meant to be sort of an introduction and overview. So hopefully folks can see the comments. And so I've posted both the Pigeonhole link for any Q&A. So I'll be monitoring that. If you have any questions for discussion, we'll have some time blocked off at the end of each presentation to address any questions from the audience. So please direct those there. And I've also posted the link to the organization website, which has a link to both our GitHub org, where the code all lives, all the fun stuff, and also our Slack workspace, which is where kind of ongoing discussions have been happening since our Birds of a Feather last year. So I think that is all of the sort of logistical bits. Again, thank you so much for being here. And I'll kick things off by just talking a little bit about sort of context and history to kind of orient people. And then we'll kick things off. And I'm actually the first presenter as well to keep the logistics smooth. So yeah, so the JuliaMolSim GitHub organization was started a few years back, I think primarily by Christoph Ortner, who you'll hear from later, as well as Antoine Levitt, to kind of create some visibility, start to create a little bit of a community around atomistic systems, computational chemistry, molecular simulation, all of these things in the Julia language. Also to have a private registry for kind of not ready for prime time codes, but that we still want to be able to easily install and play with. And again, yeah, just to be kind of a hub for collaboration to sort of bring people together. I got connected with this via Michael Herbst, who you'll also hear from later, through a collaboration with an ARPA-E funded project that I'm involved in, after he gave a talk on the DFTK code at JuliaCon 2020. And then the two of us actually co-organized the Birds of a Feather session that happened at JuliaCon 2021, which has really been kind of the jumping off point for things like the Slack workspace and the website and the community starting to grow a little bit more in scope, which we hope that this session today will be a further beginning, further jumping off point for all of that. A big further outcome of all of that work was, part of this Birds of a Feather session was really discussing, what does this community need? What can we do? What can we bring to things beyond the sorts of ecosystems that already exist in languages like Python, that really kind of leverages the power of Julia and the sort of unique capabilities. And one thing that came out of that would be really useful would be something kind of similar to what something like the atomic simulation environment or PyMatGen does, kind of a unified representation for atomic geometries, molecular structures, all of these kinds of things that could be easily shared and used by different codes and different systems. And so Michael, myself, Joe Greener, who you'll also hear from later in the session, as well as Grigory Starkov, kind of spearheaded the development of the AtomsBase interface. And so several of the packages you'll hear from in the beginning of this mini symposium session make use of this interface, support it, and there will also be some cool stuff during the quick pitches at the end for further projects making use of this. And I think this is a really powerful thing to have, this idea of being able to, with a few simple functions, kind of represent atomic geometries in a way that can make it very easy to kind of translate to whatever internal representation a code needs to run really fast, but have this flexibility to translate very easily. And so this has enabled things like a sort of Atom.io that I believe Michael will be talking about for sort of unified file reading and writing. Pranay, during the quick pitches, will talk about the beginnings of a visualization package, which I'm personally really excited about. This was a big thing that I had hoped would come out of this, the ability to visualize atomic geometries kind of agnostic to which particular code they came out of. And of course, it also has the potential to enable interoperability between different codes. So we could imagine someday having, for example, a ab initio molecular dynamics code in Julia that perhaps uses DFTK to compute the energies and forces, and Molly.jl to actually iterate these simulations. And this should in principle be fairly easy to put together, because we can sort of, these structures can kind of talk to each other in very easy ways, which anyone who's ever tried to translate between different file formats or representations within something like a Python system can tell you how meaningful a thing that is to have. So yeah, so we really hope that this will continue to be a really exciting jumping off point, and just continue to create this kind of hub for collaboration. So again, if you're not already on our Slack workspace, take advantage of the link to join that. The pigeonhole to ask questions. Yes, Anonymous, I see your hello, just checking question. Thanks for testing that that's all working. And really excited to kick things off today. And thank you all for your attention. I'll say a little bit about kind of the logistics of the rest of the session. So we'll have, the way it's organized is we have a few talks from projects that have been using the AtomsBase interface, and in many cases this is from folks who have contributed to the development of it. So that'll be the first about hour and a half or so, followed by a few contributed community talks of packages that will hopefully someday support AtomsBase, or maybe I'm behind the times and some of them already do. We'll hear from those folks later. And then at the very end, we'll have kind of a quick pitch session. So this will be a mix of sort of shorter talks, kind of smaller kind of package advertisements, things like this, as well as kind of pitches for community projects, solicitations for help in development, for ideas, for testing, all of these kinds of things. And that's really meant to hopefully be the sort of sequel to what happened with AtomsBase last year. So I look forward to that and hearing some of those ideas contributed from the community, and hopefully some of you logged in will perhaps become contributors and collaborators on some of those projects. So that is actually about all I have in terms of introductory material. It went a little bit shorter than I anticipated, but I suspect we'll have some really good Q&A going on later that will easily take up the rest of that time. So I think what I might do is, unless any questions come through on the pigeonhole or comments on anything in the next minute or so, I might just continue onward in my own presentation. But again, thank you all for being here, and very excited to share with you all of this exciting stuff. So let me get my screen share going here. Okay, having the same problem that Christoph had before. Okay, I think that's working now. Great. All right, someone send me a private chat if that looks bad, but I think as far as I can tell from the preview, we are okay. Great, so just gonna forge ahead here. So I'm gonna talk. So I am another hat that I wear within all of this is I'm the lead developer of the Camellia ecosystem for machine learning in atomistic systems. And sort of the core of crux of this ecosystem is chemistry featurization, which I think is a really unique among tools out there for this, and I think will enable a lot of really exciting stuff in the future. So I'm going to focus the talk today on the sort of evolution of that, to give people some context on where it's been and where it is today, and hopefully where it's going in the future. So I'll present to you a brief history of chemistry featurization, as well as some lessons that have been learned along the way. In terms of ways to reach me personally, my personal website and Twitter handle are here, and via the website you can find basically any other way to reach me that you might be interested in. Cool. So this all started initially with my development of atomic graphnets.jl, which actually happened before chemistry featurization came along. It was really set up as sort of a homework assignment for myself. I was just starting to learn Julia, just starting to learn how flux.jl worked. And so I basically just re-implemented a lot of cgcnn.py in Julia with a few tweaks. I can go into detail about that if people are curious, but I'm not going to focus on that here. And essentially out of the box, it had competitive performance in terms of accuracy and pretty much blew CGCNN.py out of the water in terms of performance, which was really, really cool and gratifying, because this was before I'd really learned anything at all about how to optimize Julia code, which is a journey that I'm still on personally today. So it's very, very cool when something just kind of works out of the box like that. And that definitely, this was a big part of me catching the Julia bug, so to speak. If the slide advance will work, there we go. So chemistry featurization was born somewhat after atomic graph nets, really out of my own frustration with the kind of standard approaches to featurizing, in this case, atomic graphs, but really broadly, any kind of atomic structure. These are very sort of opaque and rigid ways of doing things. So I'm going to pick on CGCNN.py here a little bit because this is the one that I'm familiar with, but these kinds of approaches exist everywhere. So basically in CGCNN.py, it comes bundled with this atominit.json, which is basically just a bunch of bit strings inside a dictionary. And so these are different atomic numbers, and there are these long bit strings that encode, if you dig into the supplementary information of the original paper, a bunch of different features in sort of one hot vectors that have been binned in various ways. And that's what these columns are showing. And this was just very frustrating to me because it's very hard to decode, to understand what information is even there. And if you wanted to tweak this, if you wanted to, for example, drop off one of these properties, or maybe use a different number of bins for one of these continuous valued properties, this is not at all easy to do. You would have to write code from scratch to regenerate this atominit.json file. And that just seemed really clunky. It seemed like part of the package should be having the ability to do that in a very flexible way. So this is kind of what motivated the design principles underlying chemistry featurization, which are first transparency. So rather than just having this bit string sitting in a dictionary in a JSON file, I want it to be very transparent upfront, very obvious, very easy to query what information I'm encoding and how is that being encoded, with what fidelity. Flexibility, I want to be able to change that. I want to be able to include or exclude different features, change the fidelity with which I encode them, maybe construct those bins for those continuous valued features in a logarithmic way or a linear way, depending on the range of values, have all of that kind of flexibility in a very easy and configurable way. I want it to be invertible. So I want to be able to, given one of these bit strings, kind of invert it and say, with what precision have I encoded this value precisely, as I might be able to do for a categorical feature, such as, which column of the periodic table my element is in, or with what, how wide is the bin, if it's a continuous valued feature that I've had to sort of chop up into bins in some way. Versatility, I want to be able to use this same API to featurize different kinds of atomic systems, molecules, crystals, interfaces, also different representations, so atomic graphs or representations that take into account the entire 3D structure of the system. I want this API to be flexible to all of those things so that I don't have to learn a different approach every time I want to build a different kind of model or use a different kind of representation. And I want it to be extensible. So, I've focused so far on graphs primarily, but I want someone else to be able to, I want the API to be flexible enough for someone else to come along and say, I actually want to build this particular molecular fingerprint featurizer or whatever. That to all be able to kind of fit into this. So the initial concept behind chemistry featurization was that it would really be a sort of one-stop shop, kind of including all of these things inside it in one sort of big package. And this was kind of the initial concept. And so here, as of July 2020, when we first released the package, this is kind of what it looked like. So using ASE.io, so the atomic simulation environment, file reading via PyCall, we would read in a structure file, which could be anything that ASE could read. Again, this started out focused and still is to some extent in terms of the fleshed outness of the implementation, focused on atom graphs. So we would build this atoms object. There would be some sort of featurization scheme. So perhaps we're featurizing individual nodes of the graph, or we're using this weave featurizer, which includes features of pairs. This would encode the features, and then the output would be this featurized atoms object. So again, you're connected to this atoms object is all of the not only the features that we've encoded, but also the information about how we encoded them that enables that invertibility and that transparency, and that would go out and be the input to some machine learning model. And this worked reasonably well at the start. Around the end of 2020, I was fortunate to receive a fellowship from the Molecular Sciences Software Institute, or MolSI, that gave me support to work on this project pretty much exclusively for about 6 months. So that was very exciting, and that helped to push things forward. And I also, through the Julia Summer of Code, through Google, with connection with Google Summer of Code, had Anant Tazamadam come online for the project, and he was a really tremendous force in kind of ideation and helping to push things forward, and especially in chemistry featurization, but also in some of the other pieces that he worked on, was really instrumental in where the code went over the ensuing, honestly, year or so. He worked over the summer, and he's continued to help in maintaining things. And around partly through this time, we kind of branded this as the Camellia ecosystem. So this includes chemistry featurization, atomic graph nets, and other things that are still being developed. So this is meant to be the, hopefully, Julia ecosystem for machine learning with atoms. And again, kind of chemistry featurization is the gateway here, and then that would create these inputs to these other models, such as atomic graph nets. Along the way, as we worked on building out this functionality within chemistry featurization to support other kinds of features and all of these kinds of things, chemistry featurization started to get really bloated. So you'd fix one thing, the CI was broken, you fix one thing, and then you try to fix the other things, and that breaks the first thing, and it was just it was really just kind of a mess. Sorry, just making sure I can see the pigeonhole here. And we realized that having chemistry featurization by itself be this kind of one-stop shop really doesn't make sense. It makes the package tremendously difficult to maintain, especially with all of the Python dependencies and other things. And so this caused us to kind of rethink how it was structured and move to a much more, honestly, kind of more Julian, like small, nimble package. And this was also inspired by, around during this whole time, having been working on the AtomsBase package and learning a lot more about the power of interfaces in Julia and this whole, paradigm, and realizing that really chemistry featurization makes a lot more sense as an interface than as a package that has too many concrete implementations in it. So here's just a snapshot from the project.toml, where we cut out a lot of specific implementations. Notably, PyCall is gone, which was very nice for the CI to pass much more frequently. And so what does this package look like today? Today, it is mostly a very lightweight interface that has a few concrete functionalities exported in it. It does support featurization of AtomsBase systems, of course, and we critically have this kind of separation of concerns, and I think this is also somewhat unique compared to a lot of other systems that are out there for this kind of thing. So we have the notion of a feature descriptor. So this would be something like, I want to encode the atomic mass of an element, or I want to encode which block of the periodic table that element sits in, S, P, D, F, etc. That's the idea of a feature descriptor. So those two that I mentioned would be what we call element feature descriptors, where you can essentially get them from a lookup table on a single element. You could have atom feature descriptors that are still a feature of a single atom, but may depend on the environment. So perhaps the oxidation state would be an example of that, as well as, of course, pair features, bond features, and potentially even environment features that capture kind of larger scale features. So that's a feature descriptor. Then we have a codec. So this is the thing that actually does the encoding. So this could be a one-hot encoder, like I described for the graph featurization, where either if it's a categorical feature, then you just make this one-hot vector. If it's a continuous valued feature like the atomic mass, then you sort of make some choices about creating bins and build a one-hot vector that way. But you could also imagine other ways to do this. You could encode the value directly, and maybe that's with just some perhaps normalization or scaling. And that might be useful for certain applications. So in the next so those two are at the level of individual features. Then we have a featurization scheme. So that's essentially some collection of features and how, excuse me, and how you're going to combine those together, excuse me, to actually feed into some, sorry about that, feed into some model. So, maybe you create these one-hot vectors, and those get stacked together into a matrix, and that's the actual data representation that is then fed into a model. And then we have the featurized structure. So that's the thing that I showed before. So you have both the representation of the structure. So for a graph, that would be like the adjacency matrix, or maybe it's a full list of coordinates if you're representing the full structure, along with the associated set of features, again, kind of cooked up and structured in the way that they're designed to be fed straight into the model. So what's next? I have to confess there has not been substantial development between that February of this year and today. A lot of my effort has been focused on a few other things. Quick plug for my electrochemical kinetics.jl talk later this week. But in the new position that I'm starting in the fall, as I mentioned, I'll be taking on students, and I'm hoping to have a few students coming back to doing more active development on this package. And I'm excited for that. And of course, always welcome contributions. I think there's a balance to be struck here between, having this be really full featured, having all the different featurizers that one might expect implemented, and also thinking about, what can Julia bring uniquely to this, so that we're not just kind of duplicating something that for example, already exists in a package like DeepChem or one of these others that are out there. So there's kind of a balance there, but we're always open to contributions, especially if if anyone, if you're interested in using something or building something or improving our documentation or anything, very, very open to all of that. So that's all very much encouraged. To wrap up, I'll talk about a few lessons learned and or reinforced. Many of these may be quite familiar to folks. Julia interfaces are awesome. This whole paradigm, I think, between AtomsBase and this kind of redevelopment effort on chemistry featurization, it's really been emphasized to me how powerful this whole idea is. I think this Slack message from Anant, this is quite a bit longer than 7 days ago now, really kind of takes it home. We wanted to be the interface package, and then realized that we are the interface package. And that's really kind of the way forward. Really kind of sums up this realization that we had. Be willing to think big, but unashamed to start small. So as I mentioned, I'm hoping that Camellia can become a really big and powerful and full-featured system, but you have to start somewhere. So right now, we're focused on these graphs, and then and featurizing those and doing a really good job there. And we're hoping that that will have some great contributions from other folks and some students continuing to build all of this out. And then finally, sometimes writing up the description of your problem to send to the Julia Slack is enough for you to solve the problem. Hashtag rubber duck debugging, rubber duck coding. But when it's not, they'll probably still answer your question within minutes. And that's just a testament to, I think, the Julia community broadly. That's not really specific to the Julia Slack or the JuliaMolSim Slack or the Julia Discord. There's just a really great and helpful community and around, and people are so excited to contribute and help out, and that's just been tremendous. So I'm really, really grateful for all of that. Finally, acknowledgments. Thanks to ARPA-E as well as the MolSI for funding, and also to my MolSI mentors, Sina and Sam, who really helped me get up to speed with a lot of the sort of software development nuts and bolts in terms of getting CI working, getting the docs page hosted, all of these things that I was somewhat new to. I feel like I have a much stronger grounding in thanks to a lot of their help and advice. Of course, to Google Summer of Code for their funding of Anant, who's I really can't overstate how transformative and helpful he's been on a lot of different fronts of this project. Daria, my friend and adjoint wizard, a lot of the actual training of some of these models would not be working were it not for his help. To the extremely talented Cormelian for the beautiful Camellia logo that we have, and also to my postdoc advisor Venkat for supporting all of this and letting me kind of go off on some of these crazy journeys that were not always obviously relevant to what I was being funded by at first. So that's all I have. Seems like I'm more or less right on time now. Thank you all for the attention, and hopefully maybe some questions will start coming in. So far, I just see, I think oh, we have one new question coming in. Okay. What are some examples of ML models with atoms as input features, whether in research or industry use? Okay, yeah, great question. So, so one example is, as I sort of alluded to, is graph convolutional neural nets. So I'll pull up my little slide that has kind of an explainer on that. Oops, I lost the pigeonhole. There it is. So this is an example here where you would have, for example, the some atomic structure. So I guess I should clarify quickly that it's atomic features, but they're features of some overall structure. So we would build some sort of, maybe I'll go back momentarily. Suppose you have some cartoon structure like this. You can represent this as so you can think of this as a ball and stick model, like in a chemistry class. But we can represent this as a graph. So the balls here then become nodes, and the sticks, so to speak, are edges. And that graph can be an adjacency matrix. So this is a unweighted graph. In our case, we actually typically use weighted graphs where these would be some continuous value between 0 and 1 to account for features like how far away the atoms are from each other. And then we can featurize these. So if you imagine the simplest sort of feature would be just a single number on each one. So we can build the Laplacian matrix. I won't go into all of what all that is. But this idea that graph convolution kind of serves as this diffusional. It's an operation that respects the structure of the graph and kind of allows information to diffuse respecting this connectivity here. And so in this cartoon example I show, there's just a single number is the feature for each node. But if you imagine expanding this out into a matrix where you have a vector as a feature for each node, that's what typically happens in these models. And so in this case, those vectors that I was talking about before, so you might encode in something like a bit string different features or sets of features, and then feed it into a model like this. And so you in a graph convolutional neural net, you would typically have a few of these convolutional layers, and then there's some kind of pooling operation to get to a consistent length feature vector, and then some feed forward, just typical densely connected layers out to one or perhaps several outputs, depending on if you're doing a kind of regression or a classification problem. So hopefully that addresses that question. That's one example. That's an example that I've been working with pretty extensively, but there are other examples out there as well. One area that I'm really excited about and hope to get started working in is some of these equivariant models where you actually represent the full structure. Excuse me, and you can build a model that respects not only the connectivity of the structure the way that a GCN does, but also aspects. So for example, if you represent the 3D structure in some set of coordinates, if you just rotate that coordinate system in an equivariant model, you can guarantee that the output, if the output is some sort of vectorial or tensorial quantity, it will rotate appropriately or be invariant to that kind of rotation, while still retaining more structural information than the sort of flattening into a graph necessarily does. And that's another kind of model where you would have features of individual atoms as input to that. So hopefully that addresses your question, Sundar. Thanks for asking it. And we've got another minute or so if anyone has any other questions they want to pop in. Let's see, I think that, okay, I don't see anything else on the pigeonhole. Oh, there's a couple more that popped in here. Okay. Can you represent chirality? That's so, yeah. in a typical graph model, no, you cannot. That is definitely a big shortcoming. There's actually a lot of interesting papers. Feel free to Slack me and I can point you to some of them talking about the shortcomings of different kinds of representations and what sorts of features you can or cannot capture. So yeah, that's a big one. In a traditional graph model, you can't. There are some newer kind of emerging approaches where you can capture features like that, and that's, I think, a really interesting area. Has there been papers using this package? So there are not any published papers yet. That is something that will hopefully change in the relatively near future. Yeah, that's kind of the short answer there. Documentation and tutorials, yes, thank you. If you go to camellia.org, that's the quickest and most and easiest to remember URL for that, and that will link to the Camellia has its own GitHub organization, which should link you to all of the documentation for all of this stuff. And please, 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 if you find something out of date or incorrect in the documentation, do not hesitate to file an issue. I want all of that to be up to date and helpful for people. And we've got some good stuff up there now with sort of Pluto notebooks to step through things and a lot of different examples. So that is pretty much my time. So I am going to stop sharing my screen and turn things over here to Joe. Let me add him and his slides to the stream. Hang on, sorry, I am all over the place here. Okay, beautiful. All right, I think you are live, Joe, and take it away.
Great, thanks a lot, Rachel. And I'd just like to say, this is a great idea to have this, symposium bringing together the community. We've seen so much development in, just 1 year. So let's try and do this regularly and keep building this community. So I'm going to speak to you about Ollie, which is a molecular simulation package in Julia. I started it about maybe two and a bit years ago, 3 years ago or something, just as a way to kind of learn, basically, to learn Julia and to learn molecular dynamics. And since I moved to the LMB in Cambridge, I now get to work on this or do research with this package full time. So it's seen a lot of development on my side, and it's also seen a lot of development from a number of other people, which is fantastic. So I suspect most of you heard of molecular dynamics given the topic of the talk, but basically you set up a physical system with coordinates and velocities, and you define the rules that determine the forces in the system, and then you kind of just press play and you let the system run. I know the Julia community has a lot of differential equations people in it, so from that perspective, you're basically just numerically integrating the second order differential equation defined by F equals ma. And this is often very computationally expensive. There's not really any shortcuts. If you want to study, for instance, protein-protein binding, which might take milliseconds or even seconds, you might be limited to a femtosecond time step, which means that you need to simulate 1 billion, 10 billion steps to see what you want to see, which does take a long time. But MD has been very successful. It's been around for probably half a century now, maybe 50 years or so. And it has helped us to understand processes in chemistry and biology as well as further. And it's gonna be here for the foreseeable future, and I think it's going to become even more important because compute resources just keep getting better, particularly in the GPU space. We've seen loads of innovative machine learning approaches, and for those familiar with kind of AlphaFold and the protein structure revolution, we're getting more and more starting structures. So how do you do molecular simulation? Well, there's a number of brilliant packages which have been around for many years and have big user communities. Most of them kind of fall into the same idea, where you have fast kernels under the hood to run simulations. For instance, you might have a C++ kernel for CPU, and you might have a CUDA kernel for CUDA-enabled devices. And then they have some layer on top that the user interacts with. So that could be a binary in the case of GROMACS, or you could have a Python interface like OpenMM, and they often have kind of configuration files where you declare your system parameters. I think it's fair to say most of these packages are hard to interact with all the way down, by which I mean right from the top level of user interface all the way down to the metal. And if you want to customize them, you often have to, kind of jump into the package at certain points using a certain language, which isn't often the best way to develop new simulations. And then as we look to, the last 10 years, neural networks have become predominant, and people are now starting to integrate those into molecular dynamics. And none of these packages has, support for natively differentiable simulations. So what is Molly? Well, it's a pure Julia implementation of molecular dynamics. It's one language all the way down, 100% Julia, and simulation scripts are just Julia scripts. So in terms of design philosophy, it's kind of become fairly recently, it's become closest to OpenMM, which is in Python, but has multiple kernels under the hood. And a key philosophy of the package is that when a user defines potentials or simulators, they should be just as easy to define and as fast as the features built in. Everything's defined imperatively in Julia, so there's no kind of custom script, like custom declarative languages. If you want to write a simulator, you just write a Julia function. It's differentiable with zygote. Most of the packages is differentiable, and it's kind of under very active development. It's not stable or fully covered by tests, but it's has seen a lot of development, particularly in the last few months. So what can it do? Well, you have the kind of the classic non-bonded interactions, Jones, Coulomb, gravity, Saussure, Millet. And the bonded interactions, so harmonic bonds, angles, Morse bonds, cosine angles, torsions, and position restraints. So the combination of those first 2 points lets you simulate biomolecules and gases and polymers, quite a few other systems. You can read in OpenMM and GROMACS force field files, and you can read in coordinates using Chemfiles.jl, which gives you access to a lot of different file formats. Rachel's already introduced the AtomsBase interface, so it implements that interface, so anything that's compatible with that will also be compatible with the system type in Molly. There's a few different simulators, all the kind of standard ones in wide use today for non-enhanced simulations, so Verlet, Velocity Verlet, and a very flexible logical integrator, thanks to Noé Vlasel, and energy minimization, a series of thermostats, and periodic boundary conditions in a cubic box with optional infinite boundaries, and the list goes on. So if you want to track properties throughout a simulation, you can use the logger interface, cutoff algorithms for defining what happens at long range for non-bonded interactions. We have various enable list implementations to speed up the calculation of non-bonded forces, including linking with cell list map, and we've implemented implicit solvent, generalized Born methods. It's unitful compatible all the way down, pretty much all the way down. So what that means is physical quantities, if you want them to, they can have units. So you can either run the whole system without units, in which case it's a bit of a Wild West and you have to trust that you know what you're doing, or you can run with units, which is the recommended way, and it's not any slower. And that means every physical property in the system has a unit, and if you try and add a nanometer to a picosecond, it will throw an error, and that's initially that seems a bit annoying, but actually it's really, really useful, and it's done wonders for debugging, really. It's got some analysis functions, but this Julia is a lovely language, so you can just write your own, of course. It's got basic visualization, which I'll show later with geometries, automatic multi-threading, and then has some GPU acceleration, which I'll describe as well. What it doesn't have at the minute is enhanced sampling, although that's coming soon, as I'll describe. It doesn't have constrained bonds. It doesn't have non-cubic boundaries. this is coming soon. I know this was a highly requested feature, and I'm working on it right now. Particle mesh yield summation, which is takes a kind of a reasonable fraction of time of standard biomolecular simulations. It doesn't yet have that. Hopefully, it will one day. Pressure coupling, kind of system preparation. When you want to run large, very large systems, you generally kind of decompose the space into different domains and then solve them independently. We don't have that yet, but it'd be nice to. Chemical free energy calculations for drug discovery we don't have. The API is still a bit flexible. It's still changing to find the right approach. Test coverage is going up all the time. We do have a number of quite stringent tests, but not everything is tested. And performance is currently not as good as competing software. Okay, so on the subject of testing, I mean, when you're developing an MD package, you really have to be, pay even more attention to testing than usual, because it's so easy to get out something which looks like a real simulation, but is just not what you thought it was. So currently we can simulate standard proteins with the forces, the energies, and the trajectories matching OpenMM, which in turn matches AMBER. And the gradients with zygote match finite differencing for reverse and forward mode AD. So at least for kind of simulation of standard, what you might call standard proteins without anything funky going on, it is well tested. I guess the big kicker, the crux, is that code runs much slower than widely used MD software for two reasons. First, the technical requirements of differentiability, which we're not compromising on, and also just the heavy optimization of existing software over many decades. So in particular, the GPU path at the minute broadcasts over the whole neighbor list in order to work with the zygote broadcasting, and to get around the fact that zygote doesn't allow mutation. And so this leads to very poor memory usage and GPU saturation. So the next kind of major development in the package, which I hope to look at in the next few months, is to write GPU kernels for the force summation and to integrate those with enzyme.jl, which is able to differentiate through GPU kernels. Okay, so that's long enough without some code, so let's have a look at the simulation. You can define the components individually and run. So this uses the latest release, which came out yesterday. So you set up your boundary conditions, set up some kind of constants, and then you define your set of atoms. The place atoms function just places some atoms in space without clashing. You give them some velocities according to the Maxwell-Boltzmann distribution at a given temperature. We're going to run with Leonard-Jones parameters, which is just a simple attractive repulsive potential. We're going to use this fairly standard velocity Verlet integrator with a 2 femtosecond time step, and the Anderson thermostat, which just randomly bumps particles to keep a certain temperature. And then we set up this system struct and call the simulate function. And that kind of approach of calling system and then simulate is kind of the way the package works throughout. And then we can call visualize. So this is exported this is available in the package, and it just gives you a quick geometry video of what's going on. And that simulation you saw earlier, that's the script on the left. So you can also set up simulations in an analogous way to OpenMM, but it all runs in one language. And so in this case, we read in a force field from the XML files, and then we read in the system from a PDB file and that force field. And in this case, we want to log the energies, and we want to write out a structure, so write out the trajectory. And then it's standard approach to minimize. And in this case, we don't do equilibration. You could do that with restraints, but in this case, we just give the system random velocities and then use a Longevin integrator and simulate it on multiple threads. And then it's shown in Pymon on the right. Okay, so a bit of a gallery, just some kind of quick grab bag of simulations. So peptide, you saw in the first slide, that was simulated with Molly. You can simulate diatomic gas. I said it was compatible with Unitful, and one of the nice things about that is that you can use any unit system you want. So if you want to simulate the solar system, as shown here, That's maybe 15 orders of magnitude bigger than an atom, but not a problem. You can still do that and plot it. You can train, as I'll just discuss in a minute, you can train differentiable simulations to reproduce a familiar logo. You can make and break bonds throughout the simulation, and of course you can just use the package for, you don't have to simulate, you can use it for plotting energies and the like as well. Okay, so I'll briefly describe differentiable simulation. This is the major research direction of the package. It's my own research. For those who are familiar with recurrent neural networks, the idea is you process a series of inputs via hidden states, and then using your network, and you get some output. You then compare to the true output, you obtain some loss function, and then because you've implemented this in an automatic differentiation framework, you just press dot backward, and it will give you the gradient of that loss with respect to all the parameters in your network, and you can improve the network. So differentiable simulation is analogous, except instead of inputs, you have the starting coordinates, and then instead of hidden states, you have the trajectories, so that's the coordinates and the velocities. And then at the end, you can generate whatever loss function you want. So for instance, you could compare the final coordinates to the native coordinates of a protein and get an RMSD loss. And because you've implemented an automatic differentiation framework, you click dot backward and you obtain the gradient of that loss with respect to your force field parameters. So it lets you answer the question, how do I improve the force field to reduce some loss function? So you can imagine learning to stabilize a native structure. At epoch 0, your potentials could be flat. And then as epochs of training go on, you eventually learn to counter the starting velocities. And if you want to see this approach used to learn a coarse-grained force field of proteins, you can read that paper there. So does this software exist? Well, some packages in the last 2 years have come out for this, probably most notably JaxMD and Jax, but that doesn't have protein support as of yet. TorchMD, which does have protein support, but is perhaps fundamentally limited by its PyTorch implementation. And then in the wider ecosystem, there are other differentiable physics packages as well. So Molly can do differentiable simulations, and that was a kind of key approach when developing it. So to just give you some quick numbers, speed, if you want to run, say, 3,000 atoms, as in a small peptide, you can run 1 million steps, which is about a nanosecond, and that would take 100 hours. But if you wanted to run it with implicit solvent, you could run a 15 residue protein in 14 hours or so for 1 million steps. So that's equivalent to a 1 million step neural network. And just to give you the ideas of some loss values on the right, if you take the loss of the starting structure, then this tells you that as you increase this parameter, the sigma value of nitrogen, your RMSD goes up. And as you increase the hydrogen mass, the RMSD goes up. So you can see how you could use these gradients to improve your force field. For those wondering about how this affects gradient explosion, if you use a Lungman integrator, it actually really helps to prevent gradient exploding. And so currently, it's achievable to improve all atom implicit solvent models, so that's what we're doing. So ongoing work, contributions very welcome. We're on the JuliaMolSim Slack. There's a channel there, #Molly. So JDev, who's a GSOC student, is making great progress on replica exchange. There's a pull request for that you can check out. Pranay, who's a JSOC student, is doing well on constraint algorithms. And the James Schloss and the SESMITS project at MIT are kind of taking a look at this enzyme-compatible GPU kernels, which I think are the major development of the package going forwards. Hopefully I'll get a chance to work on that as well. I'm looking at differentiable simulations. The API is going to continue to change, sorry about that. We're breaking things in order to find the right way to do it. But at some point there'll be a stable interface and there'll be a software paper. So thanks a lot to the contributors, an incomplete list of whom are listed here. Noe was just here recently and had a very productive week, adding a lot of features. Thanks to all the Julia contributors and package authors. Particularly, I have to mention Zygot, Kudo, Static Arrays, Chemfiles, Chain Rules, AtomsBase, and Unit4, which are all fantastic. The Julia and JuliaMolSim communities, OpenMM and GROMAX, which are just really nice, and I've based a lot of the design off. And then kind of my own academic acknowledgments, Stuart Shearer's group at the LMB, and David Jones' group at UCL, where a lot of this work was done. So thank you very much for your attention.
Great. Thanks a lot, Joe, for that awesome whirlwind tour of the continued progress with Molly. We have a question from Christoph. The issue with non-cubic PBC, this should only be a neighbor list issue, and I thought both neighbor lists and cell list maps support that. What is missing?
Yeah, I mean, yeah, it's coming in very soon. It's not just a neighbor list issue unless you also store the vectors with the displacement vectors with the neighbor list. As it is in Molly, you calculate the neighbor list, and every step you recalculate the displacements, and that opens up algorithms like calculating the neighbor list every 10 steps or so. So we just need the algorithms to calculate the distances in the triclinic blocks. But that, I mean, that's actually it's on a branch now. It just needs testing basically. But it's going to come in hopefully in the next 2 weeks. It should be there.
Very cool. We also have a question on YouTube from Beryl R. What method is used to compute the potential energy? Is it ab initio? If yes, is it implemented 100% in Julia, no C++ or Fortran call, or any other libraries?
Yeah, so the main focus of the package at the minute is biomolecular simulation. So it's classical molecular mechanics force fields. So just harmonic bonds and angles, Leonard-Jones, periodic torsions, and Coulomb. But you can define your own interactions. I personally haven't defined anything quantum, DFT, or ab initio ever, but I know some people are interested in doing that. So perhaps that will be in the package one day. If you want kind of more density functional stuff or ab initio stuff, probably check out DFTK and the like.
Which is a fantastic segue to the next talk. I see one more question here. Let's see. Okay, we have one more question from Christoph, and then we'll transition over to Michael. Suppose the cost of the force field is order 100 microseconds to 1 millisecond per atom, MLIPs. Would the overhead of the force field then be sufficient to make Molly comparable with LAMPS?
I don't know. I'd have to run the numbers. I think that the main barrier to LAMPS, to being comparable with LAMPS, is that we don't really do anything smart about, multi-threading in terms of doing domain decomposition or anything like that. So as soon as you go above a few thousand atoms, we don't make particularly good use of. We don't do the right thing algorithmically, I think. So I think there's a way to go before that, but there's nothing fundamentally stopping it. It's just a case of somebody doing it, I think.
Great. Thanks a lot. If anyone has further follow-up questions or just generally wants to stay engaged with the community, I'll briefly pin the link to join our Slack channel. And as Joe mentioned, there's a Molly channel over there. But to stay mostly on time, I'm going to hand it over to Michael, who's going to talk about DFTK. So it was a great segue there. Take it away, Michael.
Yeah, thank you very much, Rachel. Thanks everyone for tuning in. So indeed, my job is now to move to exactly what has been asked in the recent question, that the question of basically generating data using electronic structure theory, using ab initio methods, and in particular, I will be talking about the density functional toolkit, DFTK, a package we developed over the past few years for density functional theory simulations. And as you can see here from my affiliation, I'm actually not a simulation person primarily. I'm affiliated with the mathematics department, so my primary focus is certainly on doing simulations, but actually also understanding really the mathematics behind these simulations, and for example, in collaboration with people from multiple communities, work on improving algorithms for density functional theory. Like one thing we did here, really, I'm going to go into a bit of details later, basically improving DFT computations for mixed systems, for systems composed of metals and insulators. We did some work on error control of DFT, basically being able to get numerical error bounds for band structures. I'm not going to talk about the details here, but feel free to ask if you're interested. And actually, the main focus of my talk is really to give you some idea how the density functional toolkit, how DFTK really is intended to bridge between communities to, for example, enable questions on numerical analysis, enable some work on high performance computing, but at the same time really have a code that is useful for simulations, useful to develop new models. Now, what I want to talk about today is really give you some overview of why this whole project DFTK was started. And as you might know, density functional theory is a very prominent method in ab initio simulations and electronic structure theory, and there are already tens of packages. So you might ask the question of like, why do we even bother? Then I'll give you a brief look at some recent features we got since my JuliaCon talk 2 years ago. Basically some things we did and what we are planning to do in the future. But before I go into the details, let me maybe give you first a little bit of a motivation for doing DFT calculations, and in particular for looking at DFT calculations from a mathematical point of view, because as you might know, DFT has been around for many years. So the question is maybe like, why bother? Why bother now? And the changing aspect, in my opinion, is that over the past, let's say 10 years, 20 years, what has become very prominent is an aspect known as computational materials design. The idea here is, for example, let's say we want to develop a new catalyst for an electrochemical reaction, something that is indeed happening in the acid differentiate project that Rachel was mentioning, where I also take part. And basically what is happening there is that basically from a very simple setup already, having, let's say, transition metal host material, which is doped with a single transition metal atom on top, right? So something comparatively simple as a structural setup. One really wants to now understand systematically which combination of transition metal host plus transition metal dopant is useful to get a new a very efficient catalyst. And already this very simple design space here, doing a very quick back of the envelope setup, you get to something like a few 100,000 to 1 million of abilities to really systematically understand this design space and find do you hear me, guys? Was I just briefly disconnected?
It was skipping for a moment. It seems like it's fine now.
Oh, great. Where did you guys lose me? Just that I know where to pick up.
I think you, it was maybe like the previous 20 seconds or so.
Okay, all right. So basically the point is that having these millions of possibilities, clearly just a pure experimental route is not sufficient to enable this and to understand really systematically over this large design space what's going on. So this is really the regime of computational materials design, of really doing systematic DFT computations, for example. And really, I should say that this has been a remarkable success over the past years, with exponential growth in papers and databases that are dealing with these sort of methods. And I think it's pretty clear that this is going to be a crucial tool to tackle 21st century challenges. Now, where does DFT come in, and where does the need for mathematical investigations come in? Well, if you're doing these screening studies, there's really a lot of parameters you choose. Like basically, first of all, you typically do a whole hierarchy of DFT simulations, as I'm showing here with slightly different method. Each time you're like discarding parts of the design space, and basically at each of these levels, you have a rather complicated computational workflow, what I'm showing here on the right. And at the workflow, when you're making, let's say, screening decisions, at each of the decisions, you're changing parameters, you're asking the question like, you're asking questions with respect to certain tolerances and so on, and that throws the question into the air, like what parameters should I choose, what tolerances should I choose? And people have really come up with quite elaborate heuristics to do that, such that nowadays something like 1% of the calculations fail, but this is still thousands of failing calculations. And this is really where our mathematical work aims to come in, really to bring forward self-adapting, so from a mathematical point of view, rigorous DFT algorithms that are black box and that therefore basically automatically adapt to the systems that you are studying without any user intervention, and therefore help to really do these high throughput computations in a more reliable way. Now, of course, these questions concern multiple communities. Basically, it's a question of modeling, it's a question of physics, it's a question of mathematics to understand the algorithms, high performance computing to make calculations fast. And I mean, overall, these different communities have rather different demands. So mathematicians often look at, let's say, reduced toy models, some maybe unphysical cases, but which are interesting to get understanding, to understand how to improve algorithms, for example. Scientists really work more on the idea of the models. They don't care so much about the numerics. And of course, practical people who really want to do the computations. And this is really the crux with the existing codes. I mean, to satisfy these four different communities with different demands is quite a difficult problem, because by itself, the codes are rather complex. For example, many features are implemented, many methods. And as a result of this, you often have, let's say, 1 million lines of code and beyond. And overall, it's therefore not so easy to really, for example, go into deep algorithmic details and start tinkering, like something what a mathematician would like to do. And moreover, because codes are written in multiple languages, often like a Python interface to drive the computation, let's say, in the C++ Fortran layer to overall really make the computations fast. It's not so easy to get in and modify some details without really understanding multiple layers of the program and multiple languages. And this is where the density functional toolkit has really come in. So our goal here is to stay within Julia for pretty much everything. We have some C dependencies, but this is in fact also optional. You could really do everything in Julia now. We need to connect to different communities, which means in this particular case, you can do really simple model problems, 1D, arbitrary potentials, analytic potentials. You can really understand everything from a mathematical point of view at that level, develop new algorithms, and without switching to a new code, really apply this now to like meta GGA, response calculations, so state-of-the-art problems. And basically, you don't have to rewrite the code. You start with a small thing, and this really allows us to make progress with some of the algorithms I'm going to discuss in just a second. It's really a high productivity research framework. I should say this. It's just basically within the Julia ecosystem, a number of standard features are now available. And with 7,000 lines of code for DFT code, this is really rather small. And as I said, it's just Julia. And so, for example, what I show also later, the initial support for algorithmic differentiation, which we have now obtained in the code, has in fact been realized in 10 weeks by a GSOC student. And I don't think this would have been possible in one of the big codes, just because of the massive number of codes that people have to really go through and understand to make progress, as newcomers, I should really say. Okay, so now let me just discuss a few of the features we have recently obtained. So I've been mentioning this quest to go towards black box algorithms. So one of the things we have done is something known as adaptive damping. So if you're basically zooming in onto the DFT problem, in the end, what you're going to solve is a so-called fixed point problem. So you have something known as a self-consistent field, the SCF, which is sort of driving yourself forward to the DFT solution. And a frequent problem in these SCF algorithms is basically the so-called damping, this damping factor alpha, as well as the preconditioning, this p to the -1. The details don't matter so much for this talk. The point is that these are parameters which govern how the SCF converges, and is something you have to choose in traditional codes a priori to get going. And a big difficulty is that basically which values you should choose there depends on the system that you're modeling. And in state-of-the-art codes, it's a bit of a guessing, a trial and error approach to really move forward on these parameters until you have found something that actually works. And so the DFTK approach here is, for example, with respect to the stamping, to use mathematical insight to come forward with an automatic selection of the stamping. And basically, the point I want to show here is that on two representative systems, you see that this blue adaptive damping basically does more or less the same as fixed damping, so places where you really choose this a priori. So the key point here is to use, again, mathematical insight from toy problems to figure out this adaptive algorithm that in the end really is almost as good as the fixed, the standard traditional approaches, but really without having any parameter to ask from the user. And a similar thing we have also achieved with respect to this p to the -1, the so-called preconditioning. Again, here the difficulty is that basically which preconditioning you should choose depends on the system under study. So in particular, depends whether you have a metal, whether you have an insulator as your system. And then if you have mixture, you sort of ask the question, what should you do? And in fact, this is a long-standing problem. It's generally not clear what to do for mixed systems with metals and insulators. And again, here we have brought forward from mathematical analysis on toy systems the so-called Eldor's mixing approach, which really sort of locally looks at the system and figures out which part of the system is a metal, which part is an insulator, to really automatically and without user intervention do the right thing. And again, I show some plots here, really showing that compared to alternatives, it's really doing a great job, I would say. Now, the last thing I want to briefly pitch here is the support for algorithmic differentiation, and in particular, an aspect which is enabled by this is to understand what is really the dependence of a property that you simulate with your density functional theory code on your choice of the density functional theory model itself. So let's consider, for example, the case where we want to optimize the structural parameters of the system that we are studying. So for example, the so-called lattice constant. What you're doing there is you're really minimizing the energy that comes out of such a DFT computation with respect to these lattice constants. And now you're asking the question, how sensitive is such an optimal lattice constant with respect to the DFT model, with respect to some parameters that sit inside the definition of my DFT functional, essentially. So what we need is we need such gradients. And I mean, doing this in practice is actually not so simple, because what we have at the DFT level is really multiple layer of iterative methods. Again, I haven't really showed this in this talk, but just believe me that there's really an iterative eigensolver. The SCF is iterative. Then the lattice optimization, in this case, is also iterative. And moreover, we need rather unusual second-order derivatives to compute these guys over here. And basically, like for every quantity of interest, if you're not interested in this lattice constant, but in something else, or for every DFT model that you might consider, which changes the definition of this epsilon here, you really need to do something new. So it's sort of a bit of a combinatorial explosion. And the traditional approach to have one PhD student to implement one such derivative is not so scalable to this level. So what we wanted to really do is we wanted to use algorithmic differentiation to break this paradigm of one PhD student per derivative, to get a generic framework for DFT derivatives, and really to, for example, also allow non-experts to just implement and obtain such gradients. And indeed, this is exactly what we have obtained. So here I show some pseudo code to compute the DFT energy and to optimize basically this function with respect to the parameters. It's really close to what you would actually do in DFTK, not 100%, but very close. And now if you want to compute these gradients as you would expect from forward diff, for example, you just have to add one line of code, right? And so, I mean, in the end, it's really sort of putting it all together from the Julia tools that we have for in this case, forward diff, from the fact that DFTK really allows to be is really floating point agnostic and allows the dual numbers from forward diff to be pushed through the whole code. And at the same time, really now we have a very generic implementation for the so-called response properties that are needed in the back to compute these gradients. And this really works. So here what I'm showing is basically the lattice constant of silicon, a very simple system for a number of DFT functionals. The details don't matter so much apart from the fact that there's two parameters, kappa and beta, in these functionals. They take slightly different values. And we are asking here the question of what's the dependency of the lattice constant on these values. And so really you can get some sensitivity, some understanding of how stable, for example, is my prediction from DFT with respect to changing the DFT model itself. Okay, so the final thing I want to talk about, the recent features that we have brought forward, is basically the integration of DFTK into the ecosystem of AtomsBase. And so here, what I just wanted to briefly show you is, it's the code example here on the right. So what we recently have been working on is the so-called Atoms.io package, a package which really allows you to automatically load basically structure files in a way that it's compatible with this AtomsBase definition that Rachel has been talking about. So here you really just say, I want to load this file, and in the back Atoms.io, which I have to say is not yet public. I have some students working on this. It's their student project. When it's finished, it will become public. And in the back, basically, this Atoms.io features some selection mechanism to figure out what it should use to pass these CIF files. It gives you back something which is directly compatible with AtomsBase. In DFTK, I can now attach pseudo potentials, which I want to use to model my problem here. I can now, using the so-called DFT functionals package, DFT functionals interface, I can define my custom DFT functional in basically 4 lines of code. Just in this case, a scaled LDA functional. And you see, I now just integrate that directly into the density functional toolkit, telling the density functional toolkit to use this exchange functional I just defined in a few lines up there. I do the standard discretization, I run my SCF, and I get my answer. So you see, basically, now we have a generic interface for defining new DFT functionals outside of anything, outside of the density functional toolkit. An easy way to just load in the structures and attach the pseudo potentials, get the calculation set up and running, and in the end you get the familiar standard SCF and the standard output here. Okay, so now just one slide on future work. What we're currently working on with another Google Summer of Code student is GPU support, where our goal is really to minimize code duplication, something that Joe has also been mentioning. We want to target in particular not only CUDA, but also AMD GPUs. That's something that the community, the broader electronic structure community, has not really done so much, to the best of my knowledge. Another thing that we're targeting is adjoint mode algorithmic differentiation. I've only been showing forward mode. Adjoint mode is really on the way. If you're interested in that, Gaspar, Marcus, and Nicholas will have a talk on this next week in the main circle of JuliaCon at 12:30 UTC on Wednesday. And yeah, basically that allows really like going to larger number of parameters. Machine learned exchange correlation functionals is one prospect, for example, things we want to explore in the future. And that brings me to my conclusion. So DFTK, I hopefully demonstrated, is really bringing mathematical research to DFT applications. We have a growing user base at the moment. We are really exploring things coming from the Julia ecosystem, AD, for example, GPU computing. We're really trying to look at uncertainties, errors in DFT in various ways. And we're using now DFTK really also for teaching, for outreach. There's some workshops coming up in a few weeks on DFTK in Paris. And yeah, so really like basically using the simplicity of Julia to spread also the word to students and to people who are new to DFT. My acknowledgements, people who have funded me, in particular the Google Summer of Code and now RWTH Aachen, where I'm currently residing, people from École de Pont, with whom basically most of the work has happened, in particular Antoine Levitt, Guillaume, who's working on GPUs, Niklas Schmitz, who's working on AD mostly, same as Marcus, people from MIT and Sesmix, I'm also collaborating. Thanks for all the input, for the ideas. And with that, I really look forward to your questions. If you're interested, here are some resources for you, my talk at JuliaCon 2021, my workshop, and at the upcoming talk this year. Thank you, and I look forward to your questions.
Great, thanks so much, Michael. This is all super exciting. We have one question on the pigeonhole. Do you plan to leverage the existing chemfiles.jl in AtomsIO.jl?
Yeah, for me, I mean, AtomsIO sits in a different pocket, right? So Chemfiles is really more for... wait, you mean Chemfiles.jl? Actually, we are already using it. I'm not sure I mentioned this properly. I think I didn't. Because in fact, actually right here, we are already using Chemfiles.jl. So this, like CIF files by default in AtomIO are passed using Chemfiles. So yes, we plan to use that. And in fact, we already are. Yes.
Wonderful. I don't see anything else on the pigeonhole. I'll ask one more quick question and then we'll move on. But again, brief plug for the Slack. If anyone else wants to continue staying engaged, Michael is certainly active on there. Do I correctly infer that that you now have exact exchange support and can do hybrid functionals. I know that
that would be super awesome. The unfortunate answer is no. I mean, we don't. It's not like a first working version would probably take a few days to code up, I would say. So we have all the infrastructure there, but it's like the thing with this is to get this working competitively to existing codes, to get this working like really in a way that you can actually use it for non-trivial practical calculations is a lot of effort, because it's really not so easy. But the first working version should be quick. So, but just the fact that, you know, if we do it, we want to do it properly and we want to like investigate some ideas, mixed precision and so on. So we haven't really started this project. And since it's not really come up in the research project, we haven't really investigated it.
Got it. So those I think you showed some PBE sensitivities, no? Those came from somewhere else?
Yes, PBE indeed, yeah.
Okay.
These things down there were PBE.
Got it. Cool. All right. Well, again, here, let me pin the Slack link briefly if anyone wants to stay engaged here.
Yeah, please ask questions. I'm very happy to answer anytime. Also, please like interact on GitHub. We are very happy to answer questions on issues or something with respect to DFDK. Very happy for contributions.
Great. All right. And let's bring in Emmanuel, who's going to talk about the SESMIX project, which has been briefly alluded to already, and I'm excited to hear a lot more. Take it away, Emmanuel.
Hello, everyone. Can you hear me? Hello?
Yep, we hear you great.
Oh, okay. Sorry. My name is Manuel, and I'm a postdoc at Julia Lab. I'm working on the SESMIX project. In this presentation, I'm going to talk about the general goals of this project, and I will focus on an overview of the software we are currently developing and integrating. SESMIX stands for Center for the Exascale Simulation of Materials in Extreme Environments. The general goal is to advance the state-of-the-art in predictive simulations by connecting quantum and molecular simulations of materials with state-of-the-art programming languages, compiler technologies, and software performance engineering tools underpinned by rigorous approaches to statistical inference and uncertainty quantification. In particular, our motivating problem is to study ultra-high temperature ceramics in hypersonic flows. It is an interdisciplinary project that brings together material science, physics, mathematics, computer science, and other areas. Within MIT, it involves the Center for Computational Science and Engineering, the Computer Science and Artificial Intelligence Laboratory, and the Statistics and Data Science Center. But we have external collaborators as well. We are developing an atomistic suite for SESMIX in Julia. In general, we want to facilitate the development and accelerate the simulations in this project. We want to show that it is possible to address these simulations using a single high-level programming language without compromising performance. That is also known as the two-language problem, where typically the simulation is first developed in a high-level programming language and due to performance issues is then rewritten in an HPC language. In doing so, we want to expand the atomistic ecosystem in Julia and expand the user communities. Also, we want to contribute to a better integration of this ecosystem with state-of-the-art software. Regarding the specific goals, we want flexible or composable workflows that allow us to change different software components as needed, and new software abstractions that simplify the development. We want new interfaces and software that enables UQ-driven integration. We want to use the power of the latest developments in automatic differentiation to accelerate the implementation of uncertainty quantification methods, training, force computations, etc. We want to simplify the creation, learning, and integration of novel interatomic potentials, and we want our software integrated with other important developments such as lamps, and of course, we want to leverage key Julia features. This is our current software roadmap. We are in the second year of the project. As you can see, there are many tools involved. During this presentation, I will talk about the subset of tools we are currently implementing and integrating to generate a basic version of the workflows. An integrated ecosystem provides more alternatives to develop a simulation. The management of hardware resources is needed. Software libraries containing parallel code can fail when several of these libraries are used simultaneously, their routines end up competing for computing resources and overall performance degrades. Having more alternatives and properly managing the use of parallel resources helps to catalyze advances in our areas of interest. But it is also a challenge. Software development is becoming more and more accessible, which increases the number of tools and overlapping functionality. Furthermore, horizontal hierarchies and in large communities make it difficult to reach consensus. Currently, integration efforts are being developed. In particular, the atomic simulation environment provides a set of tools and Python modules for setting up, manipulating, running, visualizing, and analyzing atomistic simulations. Although we are building specific software for seismics, we are looking to integrate this state-of-the-art with the state-of-the-art tools developed in Julia and other technologies. Julia has many things to offer. As we know, Julia is a high-level, high-performance dynamic programming language. Addressing the two-language problem also means that domain scientists can have more control over their work, since they don't have to acquire as much knowledge about HPC and rewrite their code. Julia is committed to abstracting performance management as much as possible. Working in a single language reduces duplication of efforts and gives experts more time to work on their research. In addition, the optimized code is easy to read, which also encourages collaboration and facilitates integration. Using software composability through multiple dispatch can facilitate and therefore accelerate the development of composable workflows, as well as the definition of new machine learning potentials, which ingredients are data, descriptors, and learning method. Furthermore, multiple dispatch can also allow us to express object-oriented and functional programming patterns. Related to this, the scientific machine learning ecosystem offers packages such as Optimization Shell that brings together several optimization packages into one unified Julia interface. Differentiable programming is another important point. It allows to accelerate development by automatically calculating loss function gradients, forces, sensitivities of quantities of interest, among others. It allows to calculate gradients across multiple languages and simulation codes. And Julia has powerful automatic differentiation tools such as Enzyme or Zygot. In particular, Enzyme meets or exceeds the performance of state-of-the-art AD tools. The developments can be also accelerated using HPC and machine learning abstractions. For example, Flux makes parallel learning simple using the NVIDIA GPU abstraction of CUDA-Shell. Julia is dynamically typed, but with support for optional type declarations. It feels like a scripting language, but it can be compiled to efficient native code for multiple platforms. These were some of the things that Julia has to offer in this kind of projects. Applying composability to the atomistic ecosystem requires characterizing the software components or main features involved in their interactions. We identify what we think are the most important high-level software components involved in seismics, organized in 3 lanes or composable workflows: classical MD, ab initio MD, and classical MD with active learning. Composable workflow 1 describes the software components and relationships of a classical MD simulation. Essentially, at each time step, the force associated with each atom is calculated based on the interatomic potential and then used to calculate each new atomic position. The correctness of the force and MD calculation is analyzed and reported through the curved arrow components to the dynamics model or control component, so that this can be reported to the user or corrective actions can be taken. In addition, a composable design must guarantee the communication of all the processes. For this purpose, wrapper components represented by small circles in the figure are included in the design. The wrappers are key in this design because they allow heterogeneous software to coexist in the same workflow. Each wrapper implements a set of interfaces associated with a particular component. Composable workflow 2 depicts an ab initio MD process. It is mostly analogous to the workflow I just described, but in this case, the force calculation is provided by a DFT simulation. Composable workflow 3 presents a combination of the latter workflows. Here, potentials and forces are fitted with respect to data generated by the DFT simulator. The fitting process can be complex. For example, subsampling could be required, and therefore requires a dedicated software component as well as analysis of its inputs in terms of errors, sensitivities, etc. Furthermore, for the dynamics model component, based on the analysis of the potentials, forces, and molecular dynamics, can refit the forces in a process called active learning. We already have a talk and some information about AtomsBase. This is a package created by the people from JuliaMol. As Michael said, it's a lightweight abstract interface for representation of atomic geometries in Julia and helps in the operability of diverse atomistic tools. Our software stack depends on this package. We also already have a talk about DFT, DFT-KJL, and other tools like Quantum Expresso provide the DFT data that will be fitted. Interatomic potentials and interatomic basis potentials. These packages create abstract structures and interfaces for common empirical and machine learning or data-driven interatomic potentials. The key functionality is to provide access to energy, forces, and stresses of atomic configurations for each of the implemented potentials. Currently, the implemented potentials are Lennard-Jones, Born-Mayer, Coulomb, CBL, Morse, SNAP, a pure Julia implementation, and a wrapper to ACE or an interface to ACE1JL. New potentials are also being developed, potential for molecules and compositions of neural networks with interatomic potentials descriptors. In addition, work is being done on efficient neighborhoods and GPU parallelization, in particular defining GPU kernel for the potentials. Currently, the main dependency within this project is AtomsBase. In the example on the left, you can see the integration with AtomsBase where an atomistic configuration or system is defined. Then an empirical potential is defined and used to compute the energies, forces, and materials of the system. Finally, information about the new created types and the computation of the basis SNAP are presented. Create your own potential. Something interesting about multiple dispatch is that once you install the software packages, you can extend them. In this example, creating a new interatomic potential without the need of modifying the original package. In this case, interatomic potentials JL. Once you define your new potential, it is automatically integrated to our system. There is no need to create a PR to extend the original package. In this sense, Julia facilitates the integration of new software with the entire atomistic suite. Potential learning. This is a package for active learning of interatomic potentials. Like the other packages, it incorporates elements from differentiable programming, software composability, and HPC. In addition, it will incorporate elements from Bayesian inference and machine learning for determining optimal parameters as well as uncertainties and sensitivities. This package offers useful functions to process input data so it is ready for training. For example, read the XYZ file with the atomic configuration or system, linearize the forces, split dataset into training and testing, normalize the data, transfer the data to the GPU, define iterators, subsample the dataset, among others. Also, functions that simplifies the learning process, iterate through the epochs and choose between different optimizers. And finally, post-processing, computation of different metrics, mean absolute error, R-squared, covariances, etc., saving results and plotting. Within this project, this tool depends on AtomsBase, interatomic potentials, and interatomic basis potentials. This package is currently under refactor and integration process. Atomistic JL. This package provides an integrated workflow for MD simulations. It provides an interface to MODI and embody simulator that allows to define and run the MD simulation and post-process its results. Atomistic JL is compatible with any interatomic potential that implements the abstract interface defined by interatomic potentials JL. The code on the left shows an implementation of the composable workflow 1 that describes a classical MD simulation. It is based on an argon system with 864 atoms and Lennard-Jones as empirical potential. The example integrates AtomsBase, interatomic potential JL, and the MD uses the embody simulator. In case you want to work with MODI instead of MBS, from the user perspective, only a few changes are needed, mainly in the thermostat and the definition of the simulator. Also, this tool abstracts the generation of plots and plot of the simulation results, temperature, different energies, radial distribution functions, among others. Composable workflow 2 depicts an ab initio ND process where a DFT simulation is used to compute the forces. The choice of parameters is for demonstration purposes, and the results are non-physical. Again, switching from MBS to MOLI can be done by modifying a few lines of code. LAMPS.jl is a wrapper to LAMPS and allows direct communication without round-tripping through Python. The model allows access to a snap and execute an MD simulation. Atomistic composable workflows. This repository aims to gather easy-to-use seismics-aligned case studies, integrating the latest developments in the Julia atomistic ecosystem with state-of-the-art tools. Although this is a work in progress, some examples are ready to be used. In particular, there is a documented example about how to install the atomistic suite and fit different DFT datasets using ACE, run multiple serial parallel fitting experiments, and run an MD simulation. These are other seismic tools and feature integration efforts. In particular, there are MLP.jl and MDP.jl are very similar tools to Interatomic Potentials JL and potential learning, so we will have to integrate that. This is the work of another researcher of the project, the work we want to integrate to our suite. Caron, I think this package will be used for sensitivities in particular. You already know Enzyme, and we didn't start with the kinetic Monte Carlo yet, but there will be an integration effort as well with that. Some software engineering practices. I mentioned composable workflows. We are using GitHub, and I will show you our repository in a second. We use continuous integration, Documenter.jl, Visual Studio Code, and Pluto notebooks. This is one of the things that we want to do in order to document. We start adopting this interesting way of integrating our tools using notebooks. You can program from your browser, so you almost do not need to use the console or more sophisticated tools such as VS Code. The notebooks can provide at the same time documentation and tutorials, code, and live result. So all is in one place. Also, you can use this as a mini laboratory and change small part of the code to test your ideas. You can export the notebook as an HTML file and use it as a blog post. Finally, this feature is experimental, but you can also run your notebook in the cloud, so you don't need to install software on your computer. In case you want to see our repo, collaborate, or give us ideas, is here. Finally, some dependencies. I know my time is up, so I'm going to quickly finish here. That's it. Oh, one more thing. If you want to communicate with people from the center, you can go to this webpage and get in touch with all the people that make this project possible.
Great.
Thank you very much.
Thanks so much, Emmanuel. This was super cool to see how you guys are already kind of taking a lot of the stuff that various folks have been building and running with it. There's one question in the pigeonhole that may be better suited for perhaps a Slack discussion. Christoph is wondering about making Interatomic Potentials a community run package due to sort of concerns about things being just within individual research groups or things like that. But I think perhaps that discussion would be best had out over the Slack. I think that's a really, maybe we can
follow up this later.
Yeah, but let's discuss it. I think there's some great points there. I just see one new question. Christoph asks, any comment on Enzyme versus Zygote versus Valentine's new package? Forgot the name. I'm not certain which one that is either.
The new package, I don't know. The enzyme versus zygote. I mean, if you want to work with interatomic, machine learning interatomic potentials, and you want to use flux, flux is integrated with zygote, and enzyme is not yet integrated with zygote, with flux. So working with that, this is one of the things, because I'm not using enzyme right now, but I hope to use this package in the future, because as I said, it meets or exceeds the performance of AD tools, state-of-the-art tools.
Yeah, I've definitely heard some exciting stuff about enzyme as well. All right, cool. So let's, and I'm endeavoring to stay not too much more than 4 or 5 minutes past time. We'll bring Gustavo in here. Let's bring his screen share up. And I think we are good. So you can take it away, Gustavo.
Okay, can I?
Yeah, we hear you great.
All right, great. So first of all, happy to be here, and thank you, Rachel, for putting the work to organize this. So my presentation will be a little bit different from the rest. I figured it's a JuliaCon conference, so I want to focus really on the code and more pragmatic. So because of that, I decided to just have a notebook so we can run some code together. And you know that, when you run code in front of people, there's a lot that can go wrong. So let's just hope that I don't look like a fool here. The first thing, let me mention, so what am I presenting on? I'm presenting on Fermi. Fermi is a package, or at this point, an ecosystem of 3 main packages. They are designed so you can run ab initio quantum chemistry simulations. So by that, I mean, currently we're focused on wave function methods. So it's different from the previous presentation that you learned about DFT. And let me first walk you through the packages that we pieced together to build Fermi. So the first one is molecules. And it is a very simple package that basically deals with creating these atom structures. So right now, this is what we use instead of the AtomsBase. There's some discussion we need in order to integrate that with what the community has been developing. But this is what gives us the basic structure. So here I have some example. You can import molecules, and if you want to read, you can either read a file or just parse a string, and this string, you're familiar, XYZ, and you can just run this, and it parses into just a vector of atom objects. Okay, you can also create a molecule on top of that, but it's not mandatory, because the idea of molecules.jl is that it doesn't really need any information about the electrons. Once we go to Fermi, it's all about the electrons. So we're computing the electronic wave function. But at this point, we're just caring about the nuclei. So there are some properties that you actually only need to know the position of your nuclei to get. For example, well, I said the molecule, you can create a molecule right here, and this is what your molecule looks like, and then there's some information that is assumed about the electrons, such that you have charge and multiplicity. You can compute the repulsion between the nuclei. You can compute, for example, center of mass, and then this is something cool that have 2 colleagues working on in this point group symmetry. So you can run this on water, for example, and you get the and it finds out what is the point group that molecule belongs to. So we're doing this because the goal is to build to the point that we can actually run ab initio computations using point group symmetry, which is important if you have small systems and you really want to throw some heavy theory at it. So in that sense, I think there's a big difference from Fermi to the other packages that we've been seeing so far, because here we really focus on the molecule, vacuum, small systems, and we want to get as precise as we can in the description of the electronic behavior. Okay, and then the second package that comes after that is Gaussian Basis. And this is the package, so it uses molecules, right? It takes molecules as a dependency, and this is the package that will handle integrals. So, if you're running ab initio computations, it all boils down to integrals over some sort of basis set that you're using. In our cases, we use Gaussian basis or Gaussian functions as the building blocks of the wave functions. And there are two ways currently you can do this. You can use, we wrap, we have this wrap around the C library called libsint. It's very efficient, it's very good, and that's the default that Fermi uses. But we also have a very, very, very simple Julia library. And if you want efficiency, you should go for libsint. But if you want flexibility, you could use the Julia library. And that's what we're using, for example, at this point for automatic differentiation that I'm just going to show some very early results at the end, time allowing. All right, so Gaussian basis, you're going to import that, and you can construct a basis set just by giving me the name of the basis set. So we have many standard basis set that you can find on Basis Set Exchange, and then you just pass a molecule. Okay, there are many ways you can construct that. That's just one way, and you construct that, and you see here by default you're gonna get a spherical as opposed to Cartesian basis, and your back end will also be linked to libsint. That is just because you need to chew up the information a little bit before you can make a C call. So that's why we have backends defined at this stage. All right, and once you have your basis set, then you can just call whatever integrals you're interested in. So for example, overlap, and you call that upon your basis set object, and you get here your overlap matrix. Another one, for example, this stands for electronic repulsion integral, and we want 2 electrons on 4 centers. So that's the integral that you might be used to look at, see represented as this. Okay, and we can run that, and you get this tensor, this 2 by 2 by 2 by 2, because that's how many basis functions we have. We have only 2. Very simple example. The problem with this is that there's a lot of redundant information in this array, so it's more common that we want element-wise. By element-wise, I really mean shell-wise. Because that's how it is computed. So you can pass here the index of the shells, and it only gives you that particular element. So if you're looking for efficiency, you really don't want to compute the full array. And you see this this 1, 1, 2, 2 would be this element right here. Okay, so that's another way to call. So there are flexible ways that we want to create, so you can use this package. You can also create, so in these lines, I'm just creating an atom right here, okay? And you can create the basis function object itself. So I have basis set objects, and then I have basis function objects. And the basis function object, you only need to pass angular momentum value. You pass the values of the coefficient, the expansion coefficients, and the exponents of your primitives. Let's not waste too much time here, but you can create that. You have a cool representation of it, and you can fetch the values as you normally would for any object. And that gives you flexibility. For example, here I'm creating this vector of atoms that I showed before. It's Gaussian basis is really just calling the molecules package. And then your basis set is really the most primitive data type that is stored in there is just a vector of those with those basis functions, right? Each associated with one atom, okay? And we can run that, and you get here your very exotic basis set where you have 2 bases in one hydrogen and just one in the other one. So it gives you flexibility to do that type of thing. Now we move to Fermi. And I want to be really quick here. I'm not really going to talk about performance. We have a paper out where you can get a very academic discussion. on it. The takeaway, the take-home message here is that it performs quite well. There's hope for it, and it's nice to write code in it. We all know that because we all here kind of using Julia for a reason. But I now, first of all, let me show you. This is the basic usage of Fermi. You can define a molecule. You can set a few options, basis set. Do you want density fitting or not? Do you want to use dyes or not? And then you can just run your RHF and your results. You get a nice output with the information about the iterations and the orbital, the summary with your orbital energies and your final Hartree-Fock energy right here. We also have more refined methods, of course, the best one being the CCSD parentheses T method. You can run that, and here the output is a little bigger, but basically we'll have your Hartree-Fock being performed first, then your couple cluster iterations right here. So you do your couple cluster doubles, and then you do the perturbative correction for triples down here, and you have this refined energy. Okay, so that's the basic usage of Fermi. Now, what I really want to talk about is something that for me is one of the reasons that why Julia, when people ask the question, why would you do this in Julia? And it has to do with the flexibility and the cool way you can just extend packages, extend functions, and it all builds upon the multiple dispatch system that Julia takes as this main paradigm of the language. So in this example, I'm going to create a Hartree-Fock code, which is completely fake. You're going to see here that I'm just generating. So if you see the line, I'm taking this, which I didn't declare the type here, but it's supposed to be an integral helper. So it's just a helper to fetch integrals. And I'm running my fake Hartree-Fock by generating some random array for the orbital coefficients, some random numbers for orbital energies, and then the energy is just a sum of the orbital energies returning that. This is just, of course, just so we have something to work on here. If you want to learn how to do a proper Hartree-Fock in our Git repository, there's another notebook where you can walk through and learn how to implement a real Hartree-Fock, not this fake one right here. So you can implement that, and let's just toolbar here. We can run that. And whoops, I have a integral helper. Let's just create an integral helper. Forgot to make that capital. And as we expected, there's a bunch of random numbers. Okay. Now, oh, I was doing this down here. What a fool. But now what we really want is to integrate that to Fermi, right? That's the whole point here. And how you do this is by, that's a default thing in Julia. You're going to import the functions that you want to extend. So here there are three functions, or three, in this case, this is more like an object. And I'm going to explain how those things work together to make this nice extension possible. So let's import that. Okay. Now, this is a new Hartree-Fock. Of course, Fermi has Hartree-Fock implemented already. But we build that such that it's flexible enough that you can pick an implementation. So we can have several different implementations of the same method. Okay. For each implementation, we associate this singleton. So this very simple structure, it's an empty structure that just kind of acts as a flag. This guides the code using multiple dispatch to the right implementation. So that's what I'm creating here. I'm creating a structure, which is RHF, subtype of RHF algorithm. And this is another key step. This function that I imported here, it's something that's called the dispatch by value. So it takes a number, and depending on what that number is, it returns something. So here I'm saying if this function takes in the number 3, return this object. Okay, so we can actually try that out. Get RGF. So you can see if we put the number 1, it returns. This is the standard Hartree-Fock implementation. So if we put number 2, that's the second Hartree-Fock, which is direct Hartree-Fock. And then the third one is the one that we just created. Okay. Now here, I'm now working with this piece right here, which is how Fermi expects the Hartree-Fock to be called, is with this function which acts as a constructor for the object, the RGF object. So here I implemented 2. The first one just takes that singleton. Okay, it creates a integral helper and passes that along to this next one right here. And you can sort of read this later, but it's basically fetching a bunch of things that you need to construct the RGF object. That's all what's happening here, so I'm not going to waste too much time. And let's see now, we can, now here I'm running Fermi. I'm not running the function up there. I'm setting the RGF algorithm to number 3, and then I'm going to run Hartree-Fock. And you see, this is the line that I had right here, my fake Hartree-Fock energy. And this return this random number, and it returns right here, it's a Hartree-Fock object. Okay, so sometimes I present this to people and it go just over their heads. But the cool thing here is that I'm creating a new implementation totally orthogonal to Fermi. I never opened Fermi source code to produce this, to put this new code in there. So this is really plays with Fermi's main goal of being a development platform, so we can play around without fear of breaking everything down. And also, it's going to play well as long as we have this object right here. Fermi knows how to fetch information out of this and use in other computations. So, for example, we can do MP2 right here, and it's just going to do, to perform an MP2 computation, you need a Hartree-Fock computation. So it first runs my fake RGF, and then it goes and runs an MP2 with that. Of course, that I'm getting nonsense here because my Hartree-Fock is nonsense, but it can use, it has no problem. Another syntax that you can use for this is actually when you call this macro, it returns an object, the RGF object, and then you can pass this RGF object to the method that you're playing with, and it works the same thing. Okay, so just to finish up now, so this is the main thing that I wanted to talk about, is like how nice it is to be able to do this in Julia, right? And that's one of the main reasons I decided to stay. But another thing is a lot of people talked about, and that's something that a direction that we want to go towards. So here I have a very preliminary result of our attempt to integrate automatic differentiation into Fermi. We just got these results like yesterday or something. So this is, again, Hartree-Fock and gradients, so forces for water molecule, just using a minimal basis set. So this is by no means a benchmark. Okay, again, look at this as a very preliminary result. And this is the error against the analytical result, and also the runtime against the analytical result. Now you see the forward diff. So using automatic differentiation, not only we get something that is way more precise, in fact, it's exact compared to finite differences, but it's faster, which is something that I worried about. We don't expect that this is ever going to be as good as the analytical result, especially for Hartree-Fock, because the expressions for the Hartree-Fock gradients are very neat. It's not, you don't need to do iterations or anything. So it's impossible that AD will outperform the analytical results. But the fact that it's better than the finite differences really make us think, okay, it's worth it to pursue this for methods that getting gradients is just too cumbersome. So this is the direction that we're going towards. And I think I've been talking for 17 minutes, so I'm going to stop right here. And this is it.
Wonderful. Thanks so much, Gustavo. Just a real tour de force in terms of like cool Julia tricks with extensibility and AD and new results from yesterday. I love to see it. there's a brief discussion on the pigeonhole, which I think is another one that may be easier to move over to Slack or even just a GitHub issue around integrating molecules.jl and AtomsBase. I know there's already been some preliminary discussion on that, but I think that may not be something that makes the most sense to do live.
But let me just comment that the main difficulty that has stopped me from doing that is it's just the different needs that different packages have. For us, all we need is the position and the charge, because because we're doing electronic computations. So all we care about is like this positive point charges in space. So I think AtomsBase has more features right now, which is probably it's more than we need. So it's easier for AtomsBase to encapsulate what we have than the other way around, if that makes sense. But we certainly will discuss that and find a good.
Sure. Yeah. I mean, I think we can continue the discussion in terms of what the advantages might be. I personally think there still might be some exciting avenues, and just regarding enabling interoperability with other packages.
Yeah. Well, the first thing I want is to make sure that things work with either one.
Of course.
Yeah.
Of course.
So,
yep. Michael Herbst adds, I guess this is a more of a comment than a question kind of question. It says, quick comment regarding AD. I don't think it's impossible to get even the same speed as analytical gradients if you're willing to write the appropriate custom rules. So maybe that's worth noting if you want sort of a unified approach to doing these gradients. If you implement those behind, then
I don't have a proof for SA, but I think for Hartrafok it would be very much impossible, because when you do AD is running with during the iterations, the Hartrafok iterations. The gradients for Hartrafok, you don't run iterations. It's just a one step. It's a one shot. So I think it would be very hard to outperform that.
Fair enough. Again, I think we can. This is what the Slack is for. If people want to continue any follow-up discussions, but okay, Michael disagrees. But we can continue this perhaps. Well, not offline, but online in a different online. Again, to stay a constant or relatively constant delay behind schedule, let's switch over to Christoph here. Let me have him go live. Let's see. Okay, we need to remove Gustavo's screen. All right, I think you are ready to go, okay? Christoph. Yeah, we hear you great.
Thank you for organizing this and effectively taking over the organization, JuliaMolSim. So I should start by apologizing a bit. I'm on holiday for the last 3 weeks, and my oldest son drowned my laptop, my brand new M1. So this is kind of hacked together very last second. We just arrived back home today, so it might be a bit chaotic, but I'll do my best to keep it more or less on track. So the main project for me for the past several years now, and also part of the reason to work with Julia is this model atomic cluster expansion. So somebody asked earlier, so what kind of ML models are there for that you can do interatomic construct interatomic potentials and force field widths? And this is sort of one of the main ideas that are sort of coming up in this community. And I'll talk a bit about our work on that. So for that purpose, I'll actually first talk about what is the atomic cluster expansion, and we've already talked quite a bit about what the purpose is. So the purpose is coarse graining, of course, right? So you want to mimic a high fidelity model through some parameterized model, and at significantly reduced cost. So in the case of interatomic potentials, is effectively what you want to do is you want to start with an electronic structure model, but then you want to coarse grain away electronic structure information and only keep the mechanics, because that's the only thing you need to actually run a molecular dynamics simulation. And there are many ways nowadays how to achieve that very effectively. And the model that we've been working on is the atomic cluster expansion. I'll give a one-slide summary for that, so that people have seen this. It's a beautiful, simple model. I think it's almost an inevitable model. It's how natural it is. So the first step in this, and this is necessary to take a step, but this is common, that you do that first, is that you you have a potential energy surface. So capital R is the collection of positions of atoms. It could have other features in there as well, but I'm not going to track them on those slides. And that you first decompose it in space, that you assign to each atom a site energy, and that site energy could depend on a small atomic environment, the way interatomic potential force will always works. And so then, rather than parameterizing the total energy, you parameterize the site energy. And that's where the term atomic comes from. So how do you do this? So step one is that you project the atomic density. So the way this is often described is that you're sitting at some atom I, and then you're looking at all the neighboring relative positions, and you create a density of that, and then you project that density onto some basis. And in language of ML, you would call this an embedding. Okay, so now the problem with this embedding is that it has some features you want. For example, it is invariant under permutations of the neighboring atoms, right? So that's great, but it's not invariant yet under other symmetries, and specifically the symmetry you care about in this setting is that your site must be invariant under rotations and reflections. So that's what we mean by that. And sort of the idea on how to fix this comes from signal processing. And so what people have done there is that you first form the n correlations. And a very good reason why you have to do this that I don't have time to discuss. So that means you're taking tensor products of the energy of this density and project that tensor products of your basis functions. And in fact, in sort of my language of numerical analysis, I don't do signal processing. What you would call these objects is simply a basis of permutation invariant polynomials, provided your these functions here are polynomials. So will these be? And so, but you still don't have the invariance under rotations in there, but you can get that by simply averaging them. So you take the we now call this symmetrized n correlation. So you take the spaces of permutation invariant polynomials, you average it over all rotations and reflections, and then that gives you features, or in fact, again, in the language of numerical analysis approximation theory, a basis of permutation and O3 invariant polynomials. And using those, you can now parameterize these site energies. So that's just the basic idea. There are many, many more tricks in there. The most important one is that if you choose the right basis here, namely a tensor product in radial angular components, where the angular component is described by spherical harmonics, then this averaging can be expressed explicitly as a linear operation. And then this just uses the irreducible representation of O3. That's what the YLMs are. And there's a bit of work to really make this work effectively, but it can all be done. And so sort of that basic idea, this model that I'm showing here, that is what we've implemented and have done a lot of research on. Okay, so how I'll start with a very quick demo. I really hope you have a big screen, because I think these fonts are very small. So how do we work? How have we implemented this? This is now in ace.jl. So first, how do we describe particles, atoms, right? So we have a type called state, right? And it can have various features. For example, if, like in the slide before, the only feature an atom has is the position, then you say, okay, my state only has a position as a feature, and then here you see the state. But you might want to give it some additional features, such as the atomic number, or you could use the symbol for the species itself. You might want to give it a charge, magnetic moment, whatever. Like, so this state object here is basically just a wrapper around named tuples, and it gives you a lot of flexibility in constructing atoms or general abstract particles that have whatever features you want them to you want it to have. Okay, so now next thing we need is the embedding. So it's this the density projection, right? So on the previous slide I called this phi NLMs. So you can define this, right? You have some way to define a radial basis, the YLM basis, and then you form products. So that gives you gives the embedding for these features, right? Because because basically they're a way they're basically a way of expressing this density projection I had on the previous slide, right? That's what that was. Okay, so now we have that. From this one particle basis, from the density projection this defines, you can now create the symmetric basis, the symmetrized end correlations. We call this here symmetric basis. And so what you have to do here is you have to specify a few things. First of all, you want that your output is invariant, right? So you need to specify this embedding here, and you want to specify with respect to which group you're symmetrizing. So in fact, that there are other groups one can specify. And then you also specify which basis functions you actually want, which of these many body basis functions you really require. And so now, once you have a basis, now you can create a linear model for the site or atomic property you want, right? So you give the basis some parameters. You're just choosing random parameters rather than fitting them. So that model can now be evaluated on an atomic environment. Now, an atomic environment is simply a collection of atom positions, right? Or possibly atom positions with features. I'm not as it is here. And then you can evaluate your model on that atomic environment. And then from that's the basic starting point. Now, from this, you can then, of course, take gradients, second gradients. You can sum them up to total energies. You can do whatever you want. But this is the very basic structure. And just to show what would really happen behind here, the symmetrization with respect to permutations and O3. If I, for example, if I rotate all the positions here, right, that's what's happening here, and then I evaluate the model on the rotated positions, you get exactly the same number. Yeah. So maybe one more little comment here is the I in front. It indicates that the output is an invariant that's related to this here. Yeah. So we always keep track what properties what are the properties we're constructing, what symmetries do they have. That's that's the key point in all of this. Okay, I really think I will skip this to not waste more time. Okay, so very quickly, there's a whole suite of codes around these basic ideas. So I just showed what ASGL does. The predecessor AS1GL, which used to be called ASGL, which is more stable and sort of more user-oriented, whereas ASGL is really very much a work in progress. And has far more features, and maybe if I have time to get to that. Oh, by the way, Rachel, if you're willing to tell me, 3 minutes before I should stop, I'd be very grateful. Okay, but these are just sort of the two core packages, and around that there are several others. For example, ACE1 pack is written to be as user-friendly as possible, whereas these are really more for developers. ACE atoms, that's our interface to construct interatomic potentials. I'll show you in a second that we can't just construct invariant properties, but also equivariant properties. And with that, we can, for example, fit Hamiltonian operators. And then there's a package that supports the parameter estimation process. That's ACE fit. ACE flux is something fairly new, where we're trying to go away from these linear models and build more nonlinear models. This is again very much a work in progress. And then there's one more package I want to mention, MAZE. This is essentially the state of the art for machine learned interatomic potentials. And unfortunately, that's not written in Julia, and that's maybe part of my discussion at the very end, but it's related to everything I'm talking about. All right. So now a second demo to show a little bit about all these satellite packages. So here I want to actually fit an actual interatomic potential and just show you that you can do this with just a few lines of code. So here I'm just showing a data file, and then this is an XYZ file that uses what is called xyz.jl that reads in training data. It analyzes the training data. It gives you summaries, right? You can see here, oh, I have found two kinds of structures in there. One is called FLD TIL. The other one is called TIL T5000. I forgot what the first means, but this here means that this is aluminium training data at 5,000 Kelvin. So most likely MD data. And it contains 14 such structures in total 1,100 atomic environments, 14 energy observations, 3,378 force observations, and 126 virial observations. And that's the data to which we can fit. Okay, so we generate an ACE basis, right? So this is now a short version of what I showed you on the previous slide. Okay, which species appear? What's the body order? It's actually the correlation order, so body order -1 that you want. What's the cutoff radius? And then a few other parameters that are important. In practice, you want more than just this many body A spaces. You also want to add on a pair potential, a parameter pair potential, put it together in a single basis, and then you can start fitting. This is a short script. I don't want to go into the details, so I can move on. But basically, you specify what are the weights on the different structures. You specify what solver you want to use, what prior you want to use, and so on and so forth. And then you run some least squares fit because it's a linear model. All of this actually runs in 20 seconds on my 3-4-year-old laptop that I just dug out yesterday. So because these are linear models, this is extremely efficient. You can play with them, and they get very close to state-of-the-art accuracy. All right. So here
this would probably be about the 3 minutes to go or so we can have a little bit of time for questions and discussion afterwards.
Perfect. Thank you. And then there's machinery also to perform tests and so on and so forth. Okay, so what I'll maybe do then is skip the equivariant part, which I expected I would have to. Just a few models. So with these ACE models, you can get very accuracy, so at fairly decent performance. So here we're fitting a really state-of-the-art silicon potential. So refitting a training set developed for the GAP model, basically same accuracy but much faster. I'm going to skip the molecules. This is something that isn't yet published, but this is completely stunning for me that this can be done. And this can only be done because we have these extremely efficient, fast linear models that allow you to do sampling efficiently. And so this is now a 1, 2, 3, 4 component alloy and a fully automated construction of phase diagram for a 4 component alloy. I think maybe this is something one needs to give a full talk in more detail, but these are the sort of things we can with these you can actually do real science. That's the main point I want to make. It's not just a sort of a toy code to play around with. All right, so I'm going to skip this, but the main point is you can construct equivariant models as well, and it's as easy as invariant models. Everything is sort of made as accessible, as user-friendly as possible. I wouldn't say it's yet that user-friendly, but that's certainly our goal. So maybe just that comment. So once you can construct equivariant models, then you can, for example, fit Hamiltonian operators. This is something we've done here. So we're fitting the self-consistent DFT Hamiltonian, so that you can basically skip the SCF iteration. But there are much more exciting applications of this as well. So in 2 more recent works, so we're starting to parameterize wave functions. So we use this atomic cluster expansion to parameterize, to construct efficient wave function representations. And the last one that I'm extremely excited about, not quite the domain of this symposium, but is jet tagging. So this is analyzing experiments from super colliders. And all of this can be done within the same framework. So it's really very general and very flexible. That was the whole idea. Okay, so then what I'll do here is I'll just have a few final comments to discuss sort of what I'm thinking right now, where what we've been doing, what I found did not work so well, to maybe get some input, maybe help if anybody's interested. So the first comment was on AtomsBase. Why have we adopted that yet? Well, basically, because nobody amongst my collaborators really cared. And I didn't have the time. So that's what I'm hoping we will in the future. But before this becomes useful for us, we would really also need a community package to have prototypes, not just for apps and structures, but also for the operations you perform on them. So I really hope that we could agree on something like that. I think common interfaces. None of my collaborators use Julia to actually run simulations. They will use ASE or LAMPS, and that's about it. There was some discussion about moving to Molly. I think the general sense was this isn't ready yet for what they want to do. We'll see if we get there soon, hopefully. So I wonder if there is some energy in this community to create interfaces that we can share. I found it incredibly hard and frustrating to create robust Python and C++ interfaces. They usually run for maybe 1 million time steps, and after 2 million or 10 million crash with the second, and we have no way of finding it. The third comment I had was sort of this HGL package. I spent a lot of time over the past few months making it more composable and then differentiable. Right, and it was not easy to do this while keeping the performance that I had in my original ACE package. So this is still very much a work in progress, and I'm very interested in hearing people's experiences on AD, which way everybody's going, and then finally same on GPU. Basically, we've given up on that for now, and that's the reason why the multi-layer version of ACE that's been developed over the past few months was not written in Julia. It was very bad about that, but this was written based on PyTorch, and I hope very much that I can catch up on that. And again, I'd be very interested in hearing people's views and have a discussion about possibilities here. So I'll stop here, and if there are questions I didn't follow, then I'm happy to talk about them, of course.
Great. Maybe I'll start with the question we have in the Pigeonhole. So fairly, I guess, nuts and bolts question. How long would it take to calculate forces and energies for 1,000 atom system using ACE? Are simulations of biomolecules feasible?
Right. So biomolecules, there's a caveat in that, right? If you want to run biomolecules, I think it's a sampling problem, right? You have to optimization or something like that. So latency is a big issue, right? But let me maybe let's start with what is the cost of a high accuracy ACE model. Basically, it's in the range of 100 microseconds to 1 millisecond for the highest accuracy that you would want to achieve. If you're willing to sacrifice accuracy, you go down, of course, in cost, because it's a linear model. You pick how many features you want, that the actual scales nearly with that. But for the sort of state-of-the-art accuracy models, you have to estimate 100 microseconds to 1 milliseconds. So that's in serial on a single CPU. So once you parallelize, so you can multiply that by 1,000, right? But then if you do, then that gives you a good estimate, right? But I think biomolecules, the real issue is latency, and so if you have a large system and you need to sample, you need millions and millions of times, right? Unless the latency is right, I don't think you can do that, and we can have more discussion on that. Does that answer the question?
As far as I can tell, it does. Michael also asks, I have not so much battle-hardened experience on the Python to Julia side, but JuliaCon seems to be doing a lot better than the previous solutions. Have you tried that?
That is on my agenda very much. So we will definitely try that. I find I cannot do everything on my own, and so I'm bugging my collaborators to do this, and hopefully someone will pick them up and try it out, because they're as frustrated with the sec faults as I am. So this will definitely be one of the next things we will try.
Great. And so before we move on, I think that all the thoughts you have on this slide here, I think are so important. If you don't mind, I've taken a screenshot of it, and I was just going to drop it on the Slack, because I think there's a lot of follow-up threads here that would be really, really good for community discussion, and hopefully we can get some momentum around addressing at least some of these in the near future. I think, to me, part of the, like, there's so many subtle questions around, I mean, adopting AtomsBase, for instance, it's like, well, of course you shouldn't do it just to do it. We hope when we make AtomsBase that it's appealing enough because it enables other things. But it's on us ultimately to convince you that that's true, and then to also kind of make it as easy to adopt as possible. And I think that's true with a lot of this stuff around. Clearly there's a compelling case for things like AD, for things like these things, and so it's deciding that it's worth doing, and then also figuring out what the best approach is. And definitely, I've certainly struggled with some AD stuff, particularly in the package the around electrochemical rate modeling that I'll show later in the week. I think it's something that is, it may in along certain dimensions be really best in class in Julia compared to other things, but I think it still does suffer from being a little bit young and immature in certain ways that it's not always the easiest to actually make it happen, even if it works well once you do. And I think there's a lot of good discussions here that hopefully a lot of people in the community will engage with. So I thank you for bringing up all of these points.
Could I make a comment? And which is related to all of this before we move on. So most of us write these Julia packages as research notes. We experiment, and it's fun. We make fast progress. But to really make an impact, we need the users, and the users are not in Julia. They're not going to be here anytime soon. So I really think making what we do accessible to users, and by that having really standardized, robust interfaces to ASE and LAMS would be the start. I think that would make such a big difference. Anyways,
yeah, I think that's a great point. I mean, yeah, I'm personally extremely optimistic about Julia as a major part of the future of scientific computing, but obviously that future is not yet here. And it's if we want to get a foothold, I think you're thinking in exactly the right way. I think I'll definitely be interested to follow up on several of the ideas you have here afterwards and see if we can maybe get some community momentum around building these. I will say, at least in the AtomsBase case, probably the coding that actually built AtomsBase, and Michael can chime in here, and Joe to some extent too, probably took place over maybe 2 weeks, honestly. Like, the thing that took a long time was the discussions and figuring out, okay, what do we want it to have? What do we want it to look like? What would be, what is the most sort of flexible but still achievable thing that we can build? And I think it's those discussions that hopefully this community will help enable, and we can come to some, as you say, come to some kind of consensus and really and then move forward and actually build these things. So yeah, I absolutely agree. But let's continue a lot of this on Slack, I hope. Again, everyone please feel free to jump onto that Slack workspace if you're not already there. But for now, I'm going to hand it off to James. So we will.
Thank you.
Thank you very much, Christoph. Okay, and here is James' video and his screen. Okay, I think you are good to go, James.
Hello. Cool. Great. Well, yeah, it's great to be here. Thanks, Rachel, for organizing this. And I think, yeah, we've obviously raised some really good points so far. So, so today I'm going to talk about NQC Dynamics, which is a package that I've been working on during my PhD studies over the past probably a little over a year. And that this is based on doing non-adiabatic quantum classical dynamic simulations, which I appreciate is a fairly niche topic. So I'll give hopefully a good introduction to this so you can all follow along. So we've heard a lot about classical molecular dynamics, the kind of simulations we do in MOLI, and these rely upon a single ground state potential energy surface, which is a function of the atomic coordinates. And this relies upon the Born-Oppenheimer approximation that states that the electrons will adjust instantaneously to the motion of the nuclei. This can also be referred to as the adiabatic approximation. But in some cases, like in atmospheric photochemistry, for example, so this is like the photodissociation of ozone in the atmosphere, you can get like explicit electronic excitations due to the interaction with light. And in that case, the ground state Born-Oppenheimer classical dynamics is no longer going to accurately describe what's happening. And additionally, you can see similar non-adiabatic phenomena in scenarios like a molecule-metal interaction, where in this case, it's kind of different to the gas phase type photochemistry. You have many closely spaced potential energy surfaces due to the many electrons in the metal, and the small spacing between the states can lead to lots of like small excitations where the motion of the nuclei, the translational vibrational motion, can couple to these electron hole pair excitations. So ideally, we'd like to be able to treat these with classical simulations because we know these like scale very effectively with a number of degrees of freedom, and people have done absolutely massive classical dynamic simulations like big biomolecules and things like that. However, we need some way to be able to include these electronic excitations. So one of the most popular ways of doing this are surface hopping methods. And these involve running classical dynamics on a single potential energy surface, the same way that you do for classical molecular dynamics. But then when you enter coupling regions, you can hop to different states. And this hopping is based upon integrating the time-dependent electronic Schrödinger equation alongside the classical nuclear dynamics. So you have coupled electron nuclear motion. And then when the amplitudes become significantly large, you can hop to other states, and then that allows you to include these non-adiabatic effects. Then, in addition to these surface hopping methods, there are also mean field type methods, or Ehrenfest. And these, similarly to surface hopping, you will integrate the electronic Schrödinger equation alongside the classical dynamics. But this time, the force doesn't come from a single potential energy surface. This time, it's an average over multiple states, and this again is based on the electronic amplitudes. Another different way of doing it is these mapping Hamiltonian type methods. And these will map the electronic coefficients onto continuous classical variables. And this is quite nice because it's a very purely semi-classical method, and it allows you have a single classical Hamiltonian that you can use to drive your dynamics. And you're treating the electronic and nuclear degrees of freedom on the same footing. And then the final method I'll mention today is electronic friction. So this is focused on that molecule metal scenario that I mentioned before. And here you run classical dynamics on a single potential energy surface, but then you include the electron hole pair excitations by adding additional drag and random force like you do in Langevin dynamics. But this time the friction coefficient depends on the position and is related to the electronic structure of the metal. So all of these methods are included in NQC Dynamics. So when we created NQC Dynamics, we had a few goals in mind. One of them in particular was to kind of encourage a stronger correspondence between scientific publications and the code that is available, because at least in this field in particular, sometimes it's not entirely clear how to implement these things, and people that sometimes don't seem to be inclined to release their code. So we've tried to make publicly available implementations of a lot of popular methods, and hopefully this will encourage other people to do the same. And in doing so, we tried to keep a very modular structure so that it's easy for other people to add new stuff. And this is a nice thing about Julia, in that because you can create your new package and hack in any way you like to someone else's code and start adding extra pieces. It's very modular and will allow people to add stuff, but also retain ownership, because some people aren't entirely on board with the whole open source thing, and that's totally fine. But we've tried to facilitate that as well. And then another main goal was to make it easy to develop methods and go from small model systems to full atomistic systems, because a lot of the time people will introduce a new method and benchmark on a small model where you can get exact quantum results and see how well your method's performing. But then a lot of them never quite make it to the point of going to full atomistic systems. And I guess a lot of the barrier here could come from the fact that it's really hard to get these excited state potential energy landscapes that you need, but also the added barrier of having to re-implement your code can be another obstacle, and we've tried to remove that barrier. So now I'll give a package overview, and we'll talk about the different components and what a simulation might look like. So the first thing you have to consider, and this is the same for any classical dynamic simulation, is what are my initial positions, velocities, and then you also have to consider your electronic variables as well. So we have this initial conditions submodule where we've implemented a few things like Monte Carlo sampling or thermal Langevin dynamics. So you can generate a thermal equilibrium distribution to sample from. And at the minute, for the electronic variables, we just have you're in one state or another state. We don't have any like explicit sampling for like thermal occupations, but that's something we definitely will do in the future. So once you've got your initial conditions, you can then run your dynamics. So for our dynamics, we're using differential equations.jl, which is obviously a big success story of Julia. And we very much deeply relying on a lot of the stuff that they're doing, and our ensemble version uses their ensemble machinery as well, which is nice because it gives us a lot of the stuff they've already done, like the outputs that come out. And when you do an ensemble, you can average and reduce the outputs as you go to save you having to process lots of data after the fact. So then internally, we have this dynamics methods submodule. We're in there. That's where we're defining all the dynamical equations that differential equations expect. And then the other main component would be NQC models, which we've packaged separately. And this kind of touches on a lot of the things that have been discussed earlier about like potentials, and actually our interface is quite similar to the interatomic potentials that was mentioned earlier in the seismics. But the difference here, I guess, is that we need excited state landscapes and couplings as well. So it's a slightly different niche to some of the other things that have been mentioned, but it would be cool if we can find some kind of unified way of doing that. So to put this into practice then, I've put in a small example script of what a simulation might look like. So this is just going to be a one-dimensional two-state scattering problem, which was first tackled in this one of the original surface hopping publications. So we have a single particle with a mass of 2000, and then our model that we're going to use is a two-state model that looks like this, where these black lines are our adiabatic potentials, and the red line is the non-adiabatic coupling between them. So when our particle moves in from the left, when it reaches this region, it can hop between different states. So we've collected our parameters here, and this specifies the type of dynamics that we're going to be doing. So FSSH stands for fewest switches surface hopping, which is just a particular variety of surface hopping, which is very popular. So the next thing we need to do is specify our initial distribution. So here we have an initial momentum of 10 and a position of -5, which puts our particle about here, moving to the right. And then we kind of collect these things together in the dynamical distribution. So this type's quite useful because here we're just using a single position and velocity, but you can actually put in like vectors of different configurations, or you can have in like sampleables from distributions.jl as well. And this final argument just specifies the size of the sample. So here we've got one dimension and one atom, so it's just 1, 1. Then this bit on the end is the electronic distribution. So we're going to start in a pure state on state 1, which is why our particle's down here. And we're in the adiabatic representation, which you don't need to worry too much about, but it's just it means that we're here and not up here. So the next thing to consider is what the output of our simulation is going to be. So I've kind of cheated here a little bit in that I have a pre-made function that does exactly what I want it to do, but in theory here you can just write any Julia function that takes the differential equation solution and outputs something from it. But this like will take in the solution and give like a ones and zeros depending on whether it scatters or transmits and which state it ends up on. Then we're going to average over many trajectories, so we just add the mean here. And then because we're averaging, we need to specify like the output format that comes out. So this thing that I've made before will give us a component vector with a reflection and transmission component where each part has 2 states, because we have a 2-state system. So finally, we can run the simulation. We specify a time span, how long we want it to run for, and then we just add in everything we've already defined earlier. The only thing we're adding is that we want to do 500 trajectories. So when you run this, you'll get an output that looks something like this, where we do our 500 trajectories and it takes some length of time. And then at the end, this is the output that we get. So, I mean, this isn't particularly exciting. We've got like 0% reflection and pretty much 100% transmission on the ground state, which is the state that we started on. But if we were to redo the simulation lots of times for different incident momenta, we see that it looks a bit more interesting. So the simulation we just did was at 10, and you can see this green line, T1 transmission on the ground state is 100%. But then if we redo it at higher momenta, we see like some interesting pattern occur where we're seeing some like transmission on the excited state here, and there's a tiny little bump here with reflection on the ground state as well. And we can directly compare this to some of the plots that were in this initial publication. And although their X scale is like a log scale of energy, you can see that we're roughly reproducing the pattern. Like this blue line looks a bit like this one, and similarly for the green line. And we don't quite get the full spike here, which we see with this this red bump, but I think that's just because we're under conversion. I just took this plot from the example online. So if you are interested in seeing how exactly you create the plot, I mean, it's pretty much just doing that, the previous simulation in a loop. But yeah, so this is cool because we quite easily just recreate some published results. Obviously, it's for just a small model system, but you got to start somewhere. And really, the cool thing is that if you want to go to higher dimensional systems, the input script looks pretty much the same. You just have to modify a few things. So in the future, one of the big things I like to improve is the user experience. So in that example, hopefully it didn't seem too painful. It seemed fairly ergonomic. But obviously I'm working with just a one-dimensional system. So when you go to like atomistic systems, you do have to, at the minute, you would like go through ASE to load in your structures, and you have to convert it to the right format. So obviously the solution to this is to connect to the AtomsBase ecosystem, and I'm particularly excited about Michael's students and their Atom.ios. Hopefully they come out with something good, because I'd definitely be interested in using that. So yeah, that's something I'll definitely be doing in the future. And then I guess the eternal goal of this package will always be to add more stuff, add more methods, because I don't know, there's probably tens of methods like this out there, maybe not hundreds, but definitely lots. And I would very much be interested in including loads, so it's very easy to compare between different ones just by modifying a couple keywords here and there. So in particular, at the minute, we're working on this independent electron surface hopping, which is a variety of surface hopping that focused on these metallic systems where you have lots of electrons and you're hopping them all independently. So that's quite cool. So with that, then, I'd like to thank you all for listening. I thank people for funding my PhD project and other people in the Mauer group, particularly Oscar down here. He's been like running lots of simulations, doing lots of testing for me, so that was quite nice. And we have a paper down here if you're interested in reading about this in a more academic format. And of course, you can find us on GitHub, where we'd be very interested in contributors or comments, issues, all kinds of things. And I guess if you are interested in this kind of work, you can get in touch with our group at Warwick. Like my supervisor here, Reinhard, would probably be interested in talking to you if you're looking for a PhD or something. Cool, thank you.
Thanks a lot, James. Just so cool to see the ways in which the packages out there are growing for all different kinds of atomistic methods. So very neat to hear something in a simulation method that I am aware of, but certainly have never worked with. And
yeah, I think probably a lot of people have like heard about it at a conference. Someone mentioned it once or twice, but unless you actually in the field, it's quite easy to pass it by. It's not something like machine learning that follows you everywhere.
Yeah, absolutely. So thanks for sharing. The only thing I see on the pigeonhole right now is from Mark, who says, suggestion, contact the Rapids folks about GPU integration. I am not personally familiar with what Rapids is. But,
no, me neither, but yeah, I'll give it a Google.
I guess something to Google, yeah. Cool. Maybe I'll give another little bit in case anyone, I stuck the pigeonhole link up again in case anyone else has other questions. Obviously, I know James is on the Slack, so further follow-ups can happen there too. My cat is about to wreak havoc over here. Cool. All right. Well, thanks a lot again. I don't see any other questions coming in, so maybe we'll transition over to sort of the last phase here of these kind of quick pitches. I think Christoph has already done a phenomenal job of sort of informally kicking off some of this stuff with the wonderful points that he brought up at the end of his talk. And I've already sort of tried to seed some of these discussions over on the Slack, but maybe this can be another jumping off point for some of those. So given that I'm here and talking, maybe I'll kick it off and then kind of pass the ball over to other people. So the idea that I had just in terms of another way to sort of keep the community in touch and and continue sort of engagement and collaboration was some kind of community seminar series. And I would be very, very open to discussions around what the format should look like, how frequent it should be. I guess frequency would probably depend on sort of level of interest and engagement, but I think there have been a lot of really kind of creative formats that I've seen for these webinar series. If anyone's familiar with the SciML series that has been run out of my group, there's been a cool format there where there's sort of half talk, half like code demo. I think, you know, ongoing community discussions around some of these interface ideas and trying to sort of build consensus, I think could be another use case for those kind of touch points and check-ins. We obviously have a range of time zones represented here. I think maybe not as huge as some other collaborations. So I'm confident we could probably, at least with the crew that's represented today, hopefully find a feasible time, and if not, you know, make use of recording and okay, you're very cute, but you're a little bit disruptive right now. Make use of recordings and kind of shifting around the times and all of these things. So yeah, so that's my quick pitch. Very, very open to further discussion, kind of gauging interest, thoughts on format, all of this kind of stuff over on the Slack. I'll start a thread over there right after this for any further discussion, if anyone wants to offer any thoughts on that. And then I think since I see that he is here, I'll maybe hand it over to Pranay. He's going to talk about some preliminary efforts he's made for a visualization package based on using AtomsBase systems, which was something that I was really excited about as something that in particular that AtomsBase could enable. So I'm really excited to hear the progress that's been made and you know what ideas he might have or need for help or contributions. So with that, take it away, Pranay.
Yeah, thank you, Rachel. So my name is Pranay Venkatesh. I'm, as Joe mentioned earlier, I'm a JSOC student. I'm working on Molly.jl, and this really kind of stemmed as a byproduct of that because we had an issue with Molly working with Mackie. So what I really noticed was kind of missing in the JuliaMolSim community was this sort of fully Julia-based open source visualizer for molecules and simulations. So really kind of there are existing software for like VMD and Ovito for working with visualizations of like molecules and simulations. But I think there's still a lot of scope for improvement in terms of just keeping things well documented, sort of trying to accelerate it and keeping things open source and maybe sort of, you know, easily extending it to kind of the systems we want to work with. And also really seemed like a really nice way to extend the abilities of AtomsBase and Chemfiles. So really sort of the goal of a visualizer like this would just be to be able to have some visual construct for all the things that are registered on JuliaMolSim. So if you want to, like, for example, optimize a structure on DFTK and just maybe like look at it, you can just run a simulation, or so you can just sort of look at it with our tool. Or if you want to say run a simulation on Molly and just find out what the trajectory looks like, you can sort of use our tool again. Or if you maybe want to test some interatomic potential or some force field on Julia, maybe you can just use this tool directly. So the point really is that you don't have to work on hassles with, you know, plugins or like file writers or readers. You just have a full Julia interface. So if you have something that comes from Julia, then you can just work out of that. So I just started a very basic kind of rustic repository on GitHub called Sclera, SCLERA. You can just search for it on GitHub and you'll be able to find my repository. And it just uses Mackie to kind of just plot out molecules. And right now it doesn't have much capacity. It basically just scatters a bunch of atoms and it weighs those scattered points by the atomic masses. So right now it just works with inputs from Chemfiles and inputs from AtomsBase. And some of the so really the point is that you don't have to install separate plugins or use specialized tools or sort of work with weird file writers or readers. You can just directly use Julia and use this tool without worrying with all of those frustrations. So there's still, of course, a lot of concerns that we have since we've just started this package. So one concern, for example, was drawing bonds. So when you're working with files that have bonds specified, like mol2 files or PDB files, you have bonds explicitly specified. You can just draw lines between those points. But when you don't have bonds explicitly specified, then you might want to sort of come up with a scheme to do this. So for example, like XYZ files, or if you're working with an atoms-based system where you haven't specified the bonds, we need to come up with sort of a way to do that. And there's been some discussion, but we still want to like figure out explicitly how we want to do it. So for example, if you have a carbon-carbon, if you have two carbon atoms in your system, when do you sort of draw a single bond? When do you sort of draw a double bond? Do you need the atoms to come to a certain cutoff, or do you just want to specify it explicitly? So we just kind of need a discussion on that. So that's basically all that I have as of now, but it's just something that we need to work with the community right now, because we're hoping that people would really suggest implementations or based on what they want to see within within their Julia simulation. So if they have something with respect to a molecule, they could just use this package, and it depends on what they need. So the best way to sort of extend this and to work with this would be if maybe there was a hashtag visualization on the Slack. It would be really great, maybe. But it would just be like, if based on whatever needs are there for the community on visualization, you could just be posted on the Slack, and you could have a discussion and just work on implementing that. Because right now, I think what would be really great if just people put out the ideas of what they really need in visualization. So that's basically all I have to say with regards to this. I was just hoping to get to put this issue out there on working with visualizations in AtomsBase, so that the community can kind of get involved. So, yeah.
Great, awesome. So I put a comment with a link to the GitHub that's pinned to the screen right now.
Yeah, thank you.
Ask and you shall receive. I just created a Slack channel and invited you, Pranay, and anyone else should feel free to join. As I mentioned, this is a direction I'm really excited about. I think this is a very natural direction to go in, to have something where we can, similar to how some of us might use Oviedo or Vesta or something right now, very agnostic to file format, to what kind of system it is, be able to just plug it in. I think that's a really huge value add to the community. So thanks for kicking it off. Thanks for the creative package name, and let's hope that there will be some continued engagement either via the GitHub there or or on Slack. So thanks a lot for that. So next I will turn it over to Jose, who's going to talk a little bit about a package he's been working on, I think.
Yeah. Hi, everyone. I think I can share my screen, which I'll try now. Hope it's working. So for my PhD, I started developing Protosyn. It's a molecular manipulation simulation package, very similar to what we've been seeing today here. I actually started working on this in 2018, so a little bit before AtomsBase or perhaps even Molly. I was interested in doing protein design. So protein synthesis, hence the name. And if you've done protein design before, you probably heard of Rosetta. It's incredible software, which is written in C++ with a wrapper in Python. But we wanted to try something new, like some crazy, weird conformations, modifications, and even energy function components. And there are a lot of problems with existing tools like that. So, for example, there are low-level programming languages. They don't have very good documentation. They're also, like, for example, Rosetta is before GPU was something that everybody had available, so there's no support for that sort of technologies, and they're often like not open source. So that's why we did Protosyn. Julia seemed like a perfect fit, and it was a modern approach. It fixed the two-language problem, which existed with Rosetta. It had a growing community of users. We focused a lot on creating good documentation and tutorials. We included native support for GPU acceleration using CUDA.jl, distributed computing from Julia native stuff. Now, I'll just go quickly over the features. So this is a completely molecular manipulation suite. So we can do anything we want to a molecule, right? We can add sidechains, remove them, cut them, copy and paste them, graft parts from different proteins together. We'll be focusing on proteins, but it's not like necessarily proteins. It's agnostic and work for everything. Then we want to do simulations with this stuff, right? So we need energy functions. we have all the normal common stuff, like, restrained potentials or generalized Born solvation energy, stuff like that. But making energy functions, it is hard. It is really hard. So we wanted to give that work to someone else. We wanted this to be as easy as possible to plug and play with existing tools. For example, we implemented the REF15 energy function from Rosetta. We also did something with Torch-Ani. If you've ever heard of Torch-Ani, is a DFT trained machine learning potential on trained with using PyTorch. So we use PyCall to call that potential. And then we can do all sorts of algorithms. We do not do molecular dynamics. That's what Molly exists for. It's mostly iterated local search, Monte Carlo kind of stuff, which is a little bit different. And then, of course, there's a lot of features that I don't have much time here, so I'll just focus on the last one here, the ramified and weird structures. So it's something that we wanted to explore and we couldn't do with the other existing tools. So here we can do ramified stuff like sugar polymers, glycoproteins, cyclic peptides, non-canonical amino acids. So really like weird stuff made easy. We also use the SIM computing, which greatly increases performance, especially when we are working with smaller proteins. Normally, the overhead of putting things on the GPU actually doesn't allow for very good performance when comparing to SIM. And then finally, the documentation. It was something that we felt was really necessary, and so we really focused on having like very good examples, tutorials, and a full documentation website using documenter.jl. Now, this is just some under the hood stuff, which I won't go into very detail. This is a very quick example. We can see how we can like take parts from different proteins, craft them together, cut loops out, and then copy a new one in, and then do a quick Monte Carlo to close the loop, using Torch-Ani and generalized Born as the energy function to evaluate that loop closure simulation. So it is a complicated thing, but as you can see, it's like 20 lines of code. So I think the API is actually pretty good, I would say. Some interesting use cases include, for example, doing protein folding. Of course, that nowadays with AlphaFold, this is not very competitive, so to speak, but it is a fully physics-based energy function, and we can derive conformations down to 4 angstroms in RMSD. We actually have some newer results, which we go lower than 4 angstroms for small peptides, of course. But it showcases that the energy function and the conformational search engine is actually kind of working. So the future, we want to further develop Protocene, of course. Since the rise of AtomsBase, we've seen this as a very necessary thing to do, to integrate with AtomsBase. It is something that we would like to do in the near future. And then, of course, to grow a community, see what people are requiring, what sort of things do current solutions do not do, and that Protocene could do. We've had, for example, the non-canonical amino acids was something that was requested because existing tools couldn't do it. And in Protocene, that is super easy to implement. So yeah, I think that's it. I think I showcased Protocene more or less. Hope that made sense. It is an old, so to speak, project. Before all of these new technologies started to emerge in the Julia community, so to speak, it was like a parallel development, and also it was just me doing it for my PhD, me and my supervisor. I'll be finishing the PhD soon, so if somebody wants to take over Protocene and then develop these Monte Carlo applications for something useful, feel free to engage, and I'm always happy to talk about this stuff.
Very cool. Thanks so much, Jose. I don't personally spend too much time thinking about biomolecules, but as far as I can tell, this seems like a really cool set of features for those folks who do. Who I know there are several presenting and listening here. So very cool stuff. The other person we have giving a short presentation for this last segment is Leticia. So I will let her, I see she has an appropriate background for a bunch of computational folks. It seems like she's sitting in a server room. I will let her take it away and talk about what she's been working on. Thanks a lot for being here.
Thank you for the opportunity, Dr. Rachel Kurchin. I would like to share my screen. Is it possible?
Yep, go for it. If you start a screen share, then I can add it to the broadcast. So just yeah, go ahead. And just so you know, what you probably want is share screen. There's also a share slides option, but that requires you to upload something. So probably just share screen is the way to go.
Yeah, I cannot find the link to share my screen.
I mean, it should be. You're obviously on the StreamYard. I think there should be a button that just says share. And then there's like, when I click it, there's a couple of options that come up. There's slides, extra camera, video file, and share screen at the bottom. So if you just click share, and then hopefully there's a button that says share screen.
Oh, I think it's because I am through my mobile phone. But
Okay. All right. Well.
Okay, I can present just talking without my slides. So.
All right, go for it. Sorry about that.
Sorry for it. Thank you again for the opportunity. I would like to present today my package called Quantum Foca. It is already available in GitHub. I am just graded chemist. I just got my bachelor degree in chemistry, and I am an undergrad student in computer sciences, as you can see in my server room. The idea of the package is to solve the Schrödinger equation using the OHATA method to calculate the molecular integrals. And the most curious fact about Quantum Foca is that the name comes from an idea that I had between the two languages. I am Brazilian, and in Portuguese, a seal is a foca. And it is inspired by another electronic structure software that has a marine animal in the name. So it is a fun fact about Quantum Foca. Our focus in Quantum Foca is to solve the molecular integrals using the OHATA method by the fastest way you can find in other packages. So it is interesting because we have tests, and you can see it in the repository that Rachel has shared the link with you all in the comments. And the tests comparing Quantum Foca to calculate Hartree-Fock energies and coupled cluster energies show that Quantum Foca is faster than Orca software, which is really impressive after the new implementation of Shark module in Orca. And I have ideas for a near future. The main idea that I have is to implement the McMurky-Davison method to calculate the molecular integrals and use the AtomsBase system to interact between the Gaussian base, to interact Gaussian bases and molecules, and get the data that we need for the calculation more easily. For the calculation, you only need to provide the XYZ files, the charge of the molecule, and the spin multiplicity. It is quite easy to run. It is just import in your repo, in your Julia repo. And I am open for contributions, and I hope that you have understood the presentation. And if you have comments, questions, you can find me on GitHub, on Twitter, and all your comments and contributions in the repository are very welcome. And thank you again for the opportunity. Sorry for I really apologize for the technical problems. And it was a really good symposium. Many ideas here to share, to hear, and to learn. And really excited to contribute more in the projects of all the presenters that have showed the work. And thank you again. Okay.
Thank you so much, Leticia. Very cool. I will say, especially given there was the slight difficulty with sharing the slides there, if any speakers want to share slides or you know, code, the demo code, notebooks, whatever, feel free to send me those, and I can make I can update the org website with links to all of those resources if people want to follow up, or if you just want to put them on your own GitHub repo somewhere, we can link to that. Very flexible, whatever you'd like to do. So feel free to send those along. I've pinned the comment with the link to join the Slack again. So just to reiterate, you've heard me say this several times already in the last few hours, but if you know there's already been some amazing follow-up discussion on several of the points that have been raised over on the Slack workspace. So do get connected to engage there. Check out our GitHub org. It's just JuliaMolSim, very easy to find. And yeah, we're just about to the end of the time. So thank you again all for listening. Thanks especially to all the presenters who shared the really cool work. I'm very excited to be a part of pushing all of this forward. I you know, bumps in the road as they are, I think there's a tremendous future for Julia in this space, and I'm really excited to be a part of it with all of you. And yeah, thank you again for your attention. Let me just check the Pigeonhole one more time in case there were any final comments or questions or anything. I don't see anything, so yeah, I think that's it. Thank you all for your attention and your participation, and have a great rest of your day. Bye-bye.